In the boundless vastness of the universe, some events are so rare that they've been witnessed only about 13 times in all of recorded astronomy. Out of trillions of stars and billions of galaxies, just 13 instances, making these among the rarest cosmic occurrences ever known. They shine too brightly to be ordinary novae, yet fall short of the immense power of supernova. Their mysterious deep red glow puzzled astronomers for years, defying easy classification. Each appearance is fleeting, lasting only months before fading back into darkness. After decades of study, scientists uncovered their true nature. These rare events mark the merger of two stars into one, a breathtaking cosmic union known as a luminous red nova, one of the rarest sights in the entire universe. Having revealed the name behind one of the universe's rarest displays, the Luminous Red Nova, LRN. We now step closer to understanding what truly makes these events so extraordinary. A luminous red nova is not merely a random explosion or a dying star's final cry. It is the cosmic signature of two stars merging into one, an astronomical act of unity that blends beauty, violence, and transformation in a single breathtaking event. It represents a middle ground between two better-known types of stellar eruptions, the relatively modest brilliance of a classical nova and the catastrophic might of a supernova. LRNE bridge that gap. Not powerful enough to obliterate a star completely, yet far too energetic to be dismissed as a simple surface flare-up, they are sure a unique class of intermediate stellar explosions. Glowing faintly red as the newly merged star exhales its excess energy and matter into space. To understand them, imagine two stars locked in a gravitational dance, orbiting each other so closely that their outer layers begin to touch and mingle. Over time, their fate becomes inevitable. They spiral inward, losing orbital energy through gravitational interactions, magnetic braking, and tidal forces. When the two stars finally collide, the result is a colossal outburst, an explosion that hurls gas and dust into space while the combined remnant stars stabilize into a new single entity. This moment of merging releases a surge of energy equivalent to 10 million times the sun's output per year, yet it still falls short of the sheer violence of a supernova. Instead of annihilation, a rebirth occurs. The stars fuse, becoming one. And the resulting flare is what we see as a luminous red nova. The term nova in their name may sound misleading, as they differ fundamentally from the novae astronomers have known for centuries. In a classical nova, a white dwarf steals material from a nearby companion star, until the stolen gas ignites in a thermonuclear flash on its surface. This creates a brief, bright explosion that fades after days or weeks, but neither star is destroyed. A luminous red nova, on the other hand, originates from the physical merger of two stars, not from stolen gas or surface detonations. It's a collision of cores, an entanglement of atmospheres, and a merging of destinies. The process releases enormous gravitational energy, which heats the ejected gas and dust, producing the characteristic red glow and long-lasting brightness that distinguish LRNE from other transient phenomena. What makes these events even more captivating is their gradual evolution compared to the rapid flash of other stellar explosions. The light of a luminous red nova rises slowly, glowing first in visible light and later shifting into the infrared as the ejected material cools and condenses into dust. The visible color changes over time, deepening from pinkish orange to a dark crimson as temperatures drop. The slow metamorphosis mirrors the underlying transformation happening within, two stars collapsing into one, shedding their outer layers as they become a single, larger, and more stable star. From an astrophysical perspective, luminous red novae are vital because they offer direct observational evidence of a stellar merger, a process that has long been theorized but rarely seen. Binary systems where two stars orbit each other are common in the universe. In fact, more than half of all stars belong to binary or multiple systems. Over time, some of these pairs drift closer, losing orbital energy through gravitational waves or through drag forces inside a shared gaseous environment. Eventually, their orbits decay until they collide and merge. When this happens, the result is not destruction, but transformation. A blending of mass, angular momentum, and chemistry that creates a new kind of star. The luminous red nova is the cosmic footprint of that transformation, shining briefly as a monument to the union before fading into obscurity. The Luminous Red Nova also helps astronomers understand the intermediate stages of stellar death and rebirth, while a supernova signals the end of a massive star's life. And a classical nova represents surface instability on a white dwarf. An LRN embodies the process of stellar merger and renewal. In a sense, it's a cosmic wedding, messy, energetic, and unforgettable. The outburst marks both an end and a beginning, the end of two distinct stellar lives and the birth of a single renewed one. After the luminous display fades, what remains is a newly formed star, larger and more massive than either of its progenitors, surrounded by an expanding cocoon of dust and gas. The remnants of the merger's explosive release. Astronomers classify these events as intermediate luminosity transients, a group that also includes other puzzling cosmic flashes such as luminous blue variables and intermediate red transients. Among them, LRNE stand out for their unique combination of color, energy output, and duration. They emit light equivalent to millions of suns but over a longer time scale than typical novae, and their red hue comes from the relatively low temperature of the ejected material. Observations suggest that as the expanding gas cools to around 3,000 to 5,000 Kelvin, it begins to form dust, which in turn absorbs blue light and re-emits it as infrared radiation, deepening the red glow even further. This cooling phase marks the signature stage of an LRN's evolution, turning what was once a bright, fiery explosion into a dimming ember cloaked in cosmic dust. Despite their rarity, luminous red novae have become one of the most valuable tools for understanding how binary stars evolve and interact. Every time astronomers capture one, they get a glimpse into the moment of coalescence, the phase when two stars lose their individuality and become one. This helps refine our models of stellar structure, energy transfer, and mass loss. Moreover, the study of LRNE sheds light on broader cosmic mysteries, such as how asymmetric planetary nebulae form, how binary systems influence galactic chemical enrichment, and how stellar populations evolve in the long term. For decades, luminous red novae existed only as astronomical enigmas, peculiar red transients that didn't seem to fit into any known category of stellar explosion. Astronomers had recorded a few unusual outbursts, such as V838 Monocerotis in 2002 and M31I in the Andromeda Galaxy in 1988, but their nature remained uncertain. Were they failed supernovae, massive stars shedding outer layers, or perhaps something entirely new? The turning point came in 2008 when a star in the constellation Scorpius suddenly brightened in a way no one had quite seen before. That star was V1309 Scorpii, and its discovery forever changed our understanding of stellar evolution. Initially, V1309 Scorpii appeared as an unremarkable transient event. Astronomers noted that it brightened gradually over several weeks before reaching a spectacular peak in brightness, typical of a nova or red variable. But what followed puzzled scientists. Its spectrum showed unusually strong hydrogen emission lines at first, but as time passed, it shifted toward cooler temperatures and redder colors. The light curve, the graph showing how its brightness changed over time, did not match any known nova or supernova pattern. It was too slow, too cool, and too red. Something different was happening. As the mystery deepened, astronomers began digging through archival data. That's when they realized they had a gold mine. V1309 Scorpii had been continuously monitored for several years by the Optical Gravitational Lensing Experiment OGLE, a sky survey designed to detect variable stars. The OGLE data revealed something astonishing. Before the outburst, V1309 Scorpii was not a single star at all. It was a contact binary system, meaning two stars orbiting so closely that they shared a common outer atmosphere, almost touching each other. Over the years leading up to the explosion, the orbital period of this binary system had been shrinking. The two stars were slowly spiraling inward, losing angular momentum and inching toward an inevitable collision. The OGLE observations provided a cinematic view of the process in slow motion. Each orbit grew shorter until suddenly the brightness spiked in the 2008, signaling the moment the two stars merged into one. When astronomers compared the pre-merger data with the outburst, everything fit perfectly. The timing, the energy release, the color change, and the final disappearance of the binary signature. For the first time in human history, scientists had witnessed a stellar merger in real time. V1309 Scorpii wasn't just another nova, it was the smoking gun of a new class of cosmic events, the Luminous Red Nova. This discovery was revolutionary because it confirmed with direct evidence that stellar mergers can produce luminous red novae. Theoretical astrophysicists had long predicted such mergers, but until V1309 Scorpii, they were only models and hypotheses. The event proved that when two stars in a contact binary lose enough energy through gravitational and tidal forces, they inevitably spiral together, ejecting vast amounts of gas and dust in the process. This expelled material expands outward, cools, and glows with a deep red light, the signature of a luminous red nova. What made V1309 in Scorpii especially significant was that it linked observational data to physical cause. Before this, astronomers had struggled to explain oddities like V838 Monocerotis, which had produced a mesmerizing light echo captured by the Hubble Space Telescope, waves of light reflecting off surrounding interstellar dust, expanding outward like ripples in a pond. While beautiful, its true nature remained uncertain. But after the V1309 Scorpii event, scientists re-examined past transients and realized that many of these puzzling red explosions were likely also stellar mergers. The pieces finally fit together. The importance of this discovery extended far beyond one star. It demonstrated that stellar coalescence, two stars becoming one, is not just a theoretical curiosity, but a real and observable process in the universe. It showed that contact binaries, which make up a significant fraction of all binary systems, can end their lives in spectacular outbursts that enrich their surroundings with new material. These mergers, while rare, may have a lasting impact on the evolution of stellar populations, contributing to the diversity of star types and the complexity of galactic environments. In the aftermath of V1309 Scorpii, astronomers began systematically searching for similar events. They identified a small but growing list of candidates: M31RV V838 MON OGLE 2002 BLG, 360 M85 OT 2006-1, and more recently AT 2017 JFS and AT 2021 BLU. Each one displayed the same pattern: a gradual rise in brightness, a deep red color as the temperature dropped, and a slow fade accompanied by infrared emission from cooling dust. But none were documented as thoroughly as V1309 Scorpii, which remains the best-studied stellar merger in history. The recognition of this event as a luminous red nova reshaped our classification of stellar transients. It carved out a new category in the cosmic taxonomy, not a nova, not a supernova, but a merger burst, a term some astronomers now use to describe these glowing unions of stars. The discovery also underscored the importance of continuous sky monitoring. Without the Ogle project's meticulous data, the pre-merger behavior of V1309 Scorpii would have gone unnoticed, and its true nature might have remained a mystery. In the grand hierarchy of stellar explosions, not all outbursts are created equal. Some are small, fleeting flashes, like cosmic whispers, while others shake the very fabric of space-time with their ferocity. To truly grasp where luminous red novae, LRNE, fit in the stellar spectrum, it's essential to compare them with their more familiar cousins, novae and supernovae. Though these three phenomena share the word nova, Latin for new star, a term once used for any sudden stellar brightening, they are fundamentally different in both their physical origins and energetic magnitudes. Understanding these differences helps reveal the unique place LRNE occupy, the delicate middle ground between the modest and the catastrophic, between renewal and annihilation. Let's begin with the simplest of the trio, the classical nova. A classical nova occurs in a binary system where a white dwarf, a compact remnant of a once normal star, draws gas from a nearby companion, usually a main sequence star. Over time, the white dwarf's gravity pulls hydrogen-rich material from its partner, forming a dense layer on its surface. When the pressure and temperature at the base of this layer reach critical levels, the hydrogen ignites in a thermonuclear runaway reaction, causing the star to suddenly brighten by several magnitudes. The explosion expels the accumulated outer layer into space but leaves the white dwarf itself intact. Energetically speaking, a classical nova releases around 10 to the 38th to 10 to the 39th ergs of energy, a huge amount by human standards, yet relatively mild in cosmic terms. The temperature of the ejected material can reach tens of thousands of Kelvin, producing an initially blue-white glow that fades over a few weeks to months. By contrast, a supernova is a stellar cataclysm of unimaginable power. It signifies not renewal, but destruction. The violent death of a massive star or the explosive thermonuclear disruption of a white dwarf. In a core collapse supernova, a massive star, typically more than 8 times the Sun's mass, exhausts its nuclear fuel, causing its core to collapse under gravity. The resulting shock wave blows the star apart and releasing around 10 to the 51st ergs of energy, trillions of times more than a classical nova. The temperatures soar to billions of degrees, producing a blinding flash that can briefly outshine an entire galaxy. The explosion scatters heavy elements into space, leaving behind a neutron star or a black hole. Supernovae are among the most energetic events in the universe, their brilliance often visible across millions of light years. Nestled between these two extremes lies the Luminous Red Nova, occupying a fascinating middle ground. An LRN doesn't result from nuclear detonation or gravitational collapse, but rather from a gravitational coalescence, the merging of two stars into one. This process releases 10 to the 46th to 10 to the 48th ergs of energy, 1,000,000 times more than a classical nova, yet still 1,000 times weaker than a supernova. The difference in mechanism explains the difference in energy. Instead of thermonuclear destruction, an LRN's power comes from the conversion of orbital energy into heat and light as the two stars spiral together. When they merge, friction and tidal forces within their shared envelope eject material into space, and the release of gravitational potential energy heats this material, causing it to shine. The brightness of a luminous red nova also reflects this in-between status. Classical novae typically reach absolute magnitudes of around -8 to -10, meaning they can be about 10,000 times brighter than the Sun. Supernovae, on the other hand, can reach absolute magnitudes as bright as -19, making them billions of times more luminous. LRNI fall comfortably in between, with typical peak brightnesses around -11 to -15, depending on the mass and dynamics of the merging stars. This intermediate luminosity makes them noticeable, but not blindingly so. A subtle radiance that lingers rather than flashes. Another major distinction lies in temperature and color. While novae and supernovae often blaze with the hot bluish-white light of the high temperatures, typically exceeding 10,000 Kelvin, luminous red novae glow in softer, cooler tones. The outflowing material from an LRN quickly expands and cools to 3,000 to 5,000 Kelvin, which is why their light appears distinctly red or pink. This cooling process is a defining feature. As the expanding gas interacts with dust and molecules forming in the ejecta, shorter blue wavelengths are scattered or absorbed, enhancing the red hue. In fact, it's this characteristic color that earned them the name red novae. The red light tells a tale of transformation, a system cooling and settling after chaos, rather than burning and destruction. From a spectral perspective, the differences are equally striking. In novae, the early spectra show intense hydrogen and helium emission lines, typical of hot plasma, while supernova spectra are rich with heavy element lines like oxygen, iron, and silicon, forged in the blast of nucleosynthesis. Luminous red novae, however, begin with hydrogen emission, but soon develop molecular absorption features such as titanium oxide, TiO, and carbon monoxide, CO, signatures of cooler temperatures and molecule formation in the expanding debris. This spectral evolution from hot gas to cool molecular compounds is unique to LRNE, providing a clear fingerprint for astronomers trying to identify them among the sea of transient phenomena. Energy efficiency is another point of difference. In novae, much of the energy comes from a thermonuclear detonation localized on the white dwarf surface. In supernovae, the explosion is so extreme that it not only destroys the star, but also creates new elements in high-energy radiation, including gamma rays and neutrinos. Luminous red novae, by contrast, are powered by mechanical and gravitational energy conversion. The merger process stirs up immense internal friction, heating the envelope and ejecting it outward. The efficiency of this energy conversion is relatively low compared to supernovae, but the process is sustained longer, resulting in the light curves that evolve gradually rather than abruptly. Moreover, the timescales differ dramatically. Classical novae brighten and fade within weeks to months. Supernovae rise to peak within days and fade over months. Luminous red novae, however, often take several months to reach maximum brightness, sometimes exhibiting multiple peaks as shocks and dust formation episodes occur. Their gentle luminosity evolution, coupled with their long-lived infrared afterglow, marks another key distinction. The slow decay and persistent infrared emission testify to the extended cooling and dust formation taking place in the merger's aftermath. At the heart of every luminous red nova lies a slow, intricate, and awe-inspiring cosmic ballet, the stellar merger process. It is a dance of gravity, time, and energy that can take millions or even billions of years to reach its final act, the moment when two stars become one. This process, though violent in its conclusion, begins gracefully and almost imperceptibly. Two stars, bound by gravity in a binary system, orbit each other in an endless waltz, exchanging matter, energy, and angular momentum. Over time, invisible forces act upon them, tugging gently but persistently, slowly drawing them closer until the inevitable occurs. A collision that ignites one of the rarest and most beautiful phenomena in the universe, a luminous red nova. To understand this process, imagine two stars orbiting around a common center of mass. The balance between gravitational attraction, pulling them together, and centrifugal force, pushing them apart due to their motion, keeps them in stable orbits. However, no system in the cosmos is perfectly stable. Over time, subtle mechanisms begin to sap the system's angular momentum, the quantity that keeps the stars spinning around each other. As this angular momentum leaks away, the stars spiral inward, their orbits tightening and their separation shrinking. This is the beginning of the long road to merger. One of the primary culprits in this slow inward drift is tidal interaction. Just as the moon raises tides on Earth, the gravitational pull between two close stars deforms each of them slightly, creating bulges. These tidal bulges are not perfectly aligned with the line connecting the stars, leading to torques that gradually transfer angular momentum from the orbital motion to the star's rotation. This process, though incredibly slow, is relentless. Over millions of years, it causes the orbit to decay and the two stars to draw closer. Another critical mechanism is magnetic braking, especially when one or both stars possess strong magnetic fields and stellar winds. Charged particles streaming from a star along magnetic field lines carry away angular momentum. This loss of rotational energy gradually slows the stars and reduces their orbital separation. The closer the stars get, the stronger these effects become, creating a feedback loop that accelerates their inward spiral. As the two stars approach each other, their outer atmospheres begin to interact and merge, leading to the formation of what astronomers call a contact binary system. In such a system, the stars are so close that their gaseous envelopes touch, or even overlap, forming a shared envelope of material surrounding both stellar cores. The stars are no longer distinct entities, but rather two cores embedded in a common gaseous shroud. This configuration is inherently unstable, and it marks the critical stage before the actual merger. Within the shared envelope, frictional forces come into play. As the two cores orbit inside the common gaseous layer, they experience drag, much like objects moving through a thick fluid. This frictional drag converts orbital energy into heat, causing the envelope to expand and, in many cases, to be ejected into space. Meanwhile, the loss of orbital energy accelerates the inward spiral of the two cores. The stars begin to sink deeper into the envelope, spiraling toward one another on an ever-tightening path. This dramatic phase, known as the common envelope phase, is one of the most crucial yet least understood processes in stellar evolution. It's a chaotic, dynamic event lasting from weeks to years, depending on the system's mass and composition. The energy released during this phase can unbind and expel much of the envelope material, creating a vast cloud of gas and dust around the merging stars. The glowing debris ejected at this stage will later produce the characteristic red color and infrared emissions seen in luminous red novae. As the orbital decay continues, the star's cores finally collide and merge. This moment releases a tremendous burst of gravitational potential energy, equivalent to billions of times the sun's annual output. This energy is deposited into the surrounding envelope, heating it and driving the explosive outflow of material into space. The sudden ejection of this envelope is what we observe as the visible outburst, the Luminous Red Nova event itself. During the merger, the temperatures in the envelope rise dramatically, though not to the extremes of a supernova. The heating causes the surrounding gas to glow brightly in visible light, while the expelled material expands outward at several hundred kilometers per second. The system temporarily becomes thousands of times more luminous than the sun, a beacon visible across galaxies. Yet unlike in a supernova, the core of the new star survives. Instead of destruction, the merger results in creation, a single rejuvenated star that inherits the combined mass and angular momentum of its predecessors. After the merger, the newly formed star often rotates rapidly, its structure still settling from the chaotic infusion of mass and energy. The expelled gas continues to move outward, cooling and condensing into dust. Over months to years, this dust shroud absorbs visible light and re-emits it in the infrared, creating a long-lasting afterglow that astronomers can study long after the optical brightness has faded. What remains is not only a more massive single star, but also an expanding shell of debris, a visible scar of the violent merger that birthed it. The stellar merger process is not limited to a single scale. It can occur between low-mass stars, producing modest luminous red novae like V1309 Scorpii, or between more massive companions, yielding brighter and more energetic events like V838 Monocerotis. In extreme cases, the merger can involve a compact object such as a white dwarf or neutron star, though those events belong to other, far more violent classes of transients. But in all cases, the underlying principle remains the same. Gravitational interactions drive orbital decay, leading to coalescence, energy release, and ejections of material. From a broader astrophysical perspective, these mergers play a vital role in shaping stellar populations and galactic structure. Many peculiar stars, such as blue stragglers, stars that appear younger and hotter than their peers in old clusters, are believed to be the products of ancient stellar mergers. Thus, the same process that creates luminous red novae in the present-day universe may have been sculpting the stars we see today for billions of years. The final stages of the stellar merger process flow seamlessly into what astronomers call the common envelope phase, a short-lived yet extraordinarily transformative chapter in the life of a binary system. It is during this stage that the quiet, steady spiral of two stars becomes a chaotic storm of turbulence, heat, and light. Everything that has been slowly building over millions of years, the tidal friction, the orbital decay, the steady loss of angular momentum, culminates here in an intense and violent encounter. This is the point of no return, where two stars that once circled one another separately are drawn so close that one begins to engulf the other entirely, wrapping it in a vast, shared, gaseous envelope. At the beginning of this phase, the larger star, often a red giant nearing the end of its life, expands its outer layers until its radius grows to the point that it reaches or exceeds the boundary known as the Roche lobe, the region of space within which its gravity dominates. When this happens, material from the larger star begins to flow toward its smaller companion. If the mass transfer occurs too rapidly, the companion cannot accrete it efficiently, and instead, both stars become enveloped within a single extended atmosphere made of hot plasma and gas. From this moment onward, the binary system ceases to exist as two distinct stars. They are instead two cores orbiting inside a common shroud of matter, the common envelope. Inside this envelope, physics becomes brutal and beautiful. The friction between the two cores and the surrounding gas acts as an enormous energy converter. As the cores continue their orbital dance, they plow through the dense gas, losing orbital energy and angular momentum to drag forces. This energy transfer heats the envelope dramatically, creating an expanding bubble of turbulent plasma. The process is similar in concept to an object moving through a thick fluid. It slows down due to resistance, and in doing so, it transfers its kinetic energy to the surrounding medium. But in the case of a common envelope system, the scale is cosmic. The energy involved is enough to power an explosion visible across vast regions of space. The friction and drag within the envelope also act as a catalyst for coalescence. As the cores spiral inward, their orbital separation decreases at an accelerating rate. What began as a gentle gravitational drift becomes a runaway cascade, with each orbit faster and tighter than the last, within a matter of months to years. An instant compared to the billions of years of previous evolution, the two cores draw together, their orbits collapsing into one. The energy released during this inward plunge can reach up to 10 to the 47th or 10 to the 48th ergs, enough to blow away much of the envelope in a spectacular eruption. This ejected material will later cool, expand, and form the glowing shell of gas and dust that gives a luminous red nova its distinctive appearance. But not all of the envelope escapes immediately. Some of it remains bound to the merged star, forming a thick, turbulent atmosphere that gradually settles over time. As the dust condenses and cools, it begins to absorb the bluer wavelengths of light, scattering them and re-emitting the energy in the infrared spectrum. This is why luminous red novae glow with such a deep crimson hue. The visible light comes from the heated, ejected cume, while the infrared light emerges from the dust cocoon left behind. From an astrophysical standpoint, the common envelope phase is one of the least understood yet most crucial processes in binary evolution. The physics involved is so complex, combining hydrodynamics, radiation transfer, and magnetism, that even the most advanced computer simulations struggle to capture it fully. What we do know, however, is that this stage determines the fate of countless stellar systems. In some cases, the envelope ejection is so efficient that the two cores survive as a tight binary system, such as a pair of white dwarfs or neutron stars, which may later merge again in a more dramatic explosion like a kilonova or type 1 a supernova. In other cases, particularly for systems like those that produce luminous red nova, the two cores merge completely, forming a single rejuvenated star surrounded by an expanding halo of matter. This phase also explains the smooth transition from the merger process to the luminous red nova outburst itself. As the envelope is ejected and the merger nears completion, the system's brightness begins to climb. The expanding gas radiates in visible wavelengths, producing the initial rise in the light curve. As the envelope continues to expand and cool, it becomes increasingly dominated by red and infrared light. Eventually, as the envelope disperses into space, the light begins to fade, signaling the end of the visible eruption, but not the end of the transformation. The remnant star, though hidden behind dust for a while, will continue to evolve internally, adjusting to its new mass and composition. The common envelope phase, then, is more than just a step in the merger. It is the crucible where the luminous red nova is born. The frictional heating and energy transfer that occur within the shared atmosphere are directly responsible for the luminous display we observe. Without the common envelope interaction, the merger would be a relatively silent affair, invisible across cosmic distances. Instead, this phase turns the event into a celestial spectacle, a brief but brilliant signal of stellar rebirth. Observationally, evidence for the common envelope phase comes from the shape and behavior of the light curves of luminous red novae. Many show multiple peaks or plateaus in brightness, thought to correspond to different stages of the envelope's expansion and ejection. Some even exhibit sudden dips followed by rebrightenings, possibly caused by dust formation within the outflow. Infrared observations, such as those made with the Spitzer Space Telescope and other instruments, reveal the warm dust left behind, a glowing fingerprint of the envelope that once surrounded both stars. Astrophysicists continue to study this phase with intense interest, as it holds the key to understanding not only luminous red novae, but also many other cosmic phenomena. The merging of compact objects, the formation of certain types of binary black holes, and even the asymmetrical shapes of planetary nebula may all trace their origins back to a common envelope episode. This brief stage of chaos occurring in the heart of a dying binary shapes the evolution of stars and their remnants in ways we are only beginning to comprehend. As the common envelope phase reaches its turbulent climax and the two stellar cores finally merge, the event unleashes a colossal surge of energy, the defining moment that transforms a hidden stellar collision into a luminous red nova visible across the depths of space. This energy release is the engine behind everything we observe. The sudden brightening, the expansion of gas and dust, the shift in color from golden white to deep red, and the months-long afterglow that lingers in infrared light. Yet to truly grasp the scale of what unfolds, one must appreciate the staggering numbers involved, and the delicate balance that places luminous red novae between the modest flicker of novae and the cataclysmic fury of supernovae. The total energy released during a luminous red nova is estimated to be between 10 to the power of 46 and 10 to the power of 48 ergs. To put that in perspective, a single erg is a minuscule unit, roughly the energy required for a mosquito to flap its wings once. But 10 to the power of 48 ergs? That's equivalent to the sun's entire output over about 10,000 years, released in a matter of months. Is energy enough to heat trillions of planets or power every human civilization on Earth for eternity? And yet, in cosmic terms, this is a relatively gentle event. A classical nova, for comparison, typically releases about 10 to the power of 38 to 10 to the power of 39 ergs, making a luminous red nova nearly 1,000,000 times more powerful. Meanwhile, a supernova, the death throe of a massive star, can unleash around 10 to the 51st ergs, or 1,000 times greater still. The luminous red nova thus stands proudly in the middle, a bridge between creation and destruction, embodying a quiet, graceful power rather than an all-consuming explosion. But unlike novae or supernovae, the energy of a luminous red nova doesn't come from nuclear fusion or core collapse. Instead, it originates from gravitational potential energy. The raw mechanical power released as two stars spiral together and merge. When two massive objects fall toward each other under gravity, their potential energy decreases, and that energy must go somewhere. In the case of merging stars, it's converted into heat, light, and kinetic motion. As the cores sink deeper into their shared envelope, frictional forces and drag convert orbital energy into thermal energy, heating the surrounding gas to thousands of degrees. This heat drives the expansion of the envelope, ejecting it outward into space. The outward rush of material, combined with the light from the hot, glowing gas, creates the luminous display that defines the event. Interestingly, not all of the released energy is radiated as visible light. Much of it goes into kinetic energy, accelerating the envelope's gas and dust to speeds of several hundred kilometers per second, and into infrared emission, as the expanding material cools and forms dust. In fact, luminous red novae are known for their high radiative inefficiency. Only a small fraction of the total energy becomes visible light, while the rest is stored in the motion and heat of the ejected matter. This inefficiency helps explain their relatively modest brightness despite the enormous energy budget. When astronomers observe them, they often find that the optical outburst accounts for perhaps 1 to 10% of the total energy, while the rest is hidden in longer wavelengths or carried away as kinetic motion. The way this energy is distributed gives luminous red novae their unique observational profile. The initial peak in brightness corresponds to the sudden release of energy as the envelope is expelled. A shock wave propagates through the surrounding gas, heating it to several thousand Kelvin and producing visible light. As the material expands and cools, the emission shifts from optical to infrared, marking the formation of dust grains within the ejecta. The total energy radiated during this period can be estimated by integrating the light curve over time, giving astronomers a rough measure of the event's magnitude and allowing them to infer the scale of the merger that produced it. For example, the famous V838 Monocerotis eruption in 2002 released an estimated few times 10 to the 47th power ergs, placing it comfortably within the luminous red nova range. The later event, V1309 Scorpii, discovered in 2008, released roughly 10 to the power of 46 ergs, consistent with a merger between two low-mass stars. In contrast, more energetic transients like M85OT, 2006-1 and AT, 2017 JFS, may have reached or even slightly exceeded 10 to the 48th ergs, likely involving more massive stellar systems. Despite this variation, the energy range remains distinct from both novae and supernova, confirming LRNE as a separate and intermediate class of explosions. Another intriguing aspect of the energy output is the duration over which it's released. Supernovae discharge most of their energy within seconds or minutes. A violent burst of nuclear fury that quickly fades. Luminous red novae, on the other hand, unfold over weeks or months, sometimes even longer. Their slow evolution allows astronomers to watch them change in real time, observing how their light curves develop and their spectra evolve as the ejected material cools. This gradual release is tied to the merger mechanics, because the energy is generated by orbital decay and friction rather than instantaneous collapse. It is released more gently and steadily, creating a drawn-out glowing aftermath rather than a sudden detonation. Furthermore, the energy distribution in LRNE carries deep implications for stellar evolution theory. By studying the relationship between the energy output and the mass of the merging stars, scientists can estimate how efficiently orbital energy is converted in radiation, a parameter crucial for understanding how binary stars evolve into single systems. The data gathered from these events help refine models of common envelope ejection efficiency, a key factor in predicting how often such mergers occur and what types of remnants they produce. In essence, each luminous red nova serves as a natural laboratory for testing the laws of gravitational energy conversion on stellar scales. What's even more fascinating is that the total energy of a luminous red nova often mirrors the depth of the gravitational potential well from which it emerges. The closer and more compact the merging stars, the greater the energy released when they finally collide. This explains why the brightest and most energetic LRNES tend to arise from more massive binaries, or systems that have undergone prolonged orbital decay. The correlation between brightness energy output and stellar mass hints at a kind of cosmic proportionality, a symmetry between the scale of the system and the drama of its final act. When the powerful energy released in a luminous red nova pushes outward and expels vast clouds of bone and dust into space, the once hidden merger reveals its true face, a soft deep red glow that slowly blooms and fades over time. This color isn't a poetic coincidence. It's a direct consequence of the physics of cooling, molecular formation, and light scattering that occur as the ejected material expands. To the human eye and to telescopes across the electromagnetic spectrum, a luminous red nova looks like a celestial ember, burning warmly, steadily, and beautifully against the cold backdrop of space. At the height of the outburst, the expanding material from the merger initially glows with a temperature of around 5,000 to 10,000 Kelvin, which would make it appear white or slightly yellowish. However, the expansion of the ejected gas follows the fundamental thermodynamic law of adiabatic cooling. As the gas expands, it does work against its own gravity and the surrounding vacuum, losing internal energy and thus cooling down rapidly. Within weeks to months, the temperature falls to roughly 3,000 to 5,000 Kelvin, a range that corresponds to the same reddish-orange hues we associate with the surface of a cool star or the last flickers of a dying fire. This cooling process transforms the spectral character of the outburst. At high temperatures, the gas emits primarily in blue and ultraviolet wavelengths, dominated by hot hydrogen lines and ionized metal emissions. But as the temperature drops, those high-energy emissions fade, replaced by molecular absorption bands from species like titanium oxide, TiO, vanadium oxide VO, and carbon monoxide CO. These molecules can only exist in cooler environments, and their presence is a hallmark of the late stages of a luminous red nova. As they form, they absorb and re-emit light at longer wavelengths, giving the spectrum its characteristic deep red tint. However, the red color isn't just a matter of temperature. Another key player is dust formation. As the gas continues to expand and cool, the conditions become ideal for dust grains to condense within the ejecta. These grains, composed of silicates, carbon compounds, and metallic oxides, act like cosmic filters. Dust has a strong preference for scattering shorter, bluer wavelengths of light while allowing longer, redder wavelengths to pass through, a process known as wavelength-dependent scattering or reddening. This is the same reason sunsets on Earth appear red. Shorter blue wavelengths are scattered away by air molecules, while red and orange light continues on toward our eyes. In the case of a luminous red nova, the vast clouds of freshly formed dust surrounding the remnant star perform this filtering on a cosmic scale, deepening the red hue and dimming the overall brightness in visible light. The presence of dust also changes the way the event emits light across the spectrum. Much of the energy that would have appeared as visible light becomes reprocessed into infrared radiation, as the dust absorbs high-energy photons and re-emits them at longer wavelengths. Infrared telescopes like Spitzer, WYSE, and more recently the James Webb Space Telescope are therefore critical for observing luminous red novae. They allow astronomers to see through the dusty veil that obscures these events in visible light and to track the thermal glow of the cooling material long after the optical outburst is faded. The color evolution of a luminous red nova provides one of its most distinctive signatures. In the early stages, during the initial envelope ejection, the system may appear yellowish or orange, corresponding to temperatures near 6,000 to 8,000 Kelvin. As the outflow expands, the temperature declines and the color shifts progressively toward red. By the time the event reaches its maximum brightness, the peak emission wavelength moves into the near-infrared region. Later still, as dust formation accelerates, the optical brightness decreases sharply, while the infrared brightness remains strong. This transition marks the event's metamorphosis from a visible explosion to a dust-shrouded ember, glowing faintly in the infrared spectrum. This thermal and color evolution was observed vividly in events like V838 Monocerotis in 2002. At first it appeared as a bright yellowish star, but over time it became deep red and then infrared dominated it as dust condensed around it. Hubble Space Telescope images revealed the stunning light echoes, rings of light scattering off interstellar dust surrounding the system, each expanding wavefront carrying the red-tinted memory of the eruption's earlier brilliance. Similarly, in V1309 Scorpii, the spectrum evolved from a hot, hydrogen-rich phase to a cool, dusty phase within months, with the temperature settling around 3,000 Kelvin as the ejected envelope expanded. The temperature range of 3,000 to 5,000 Kelvin is especially important because it defines the border between hot plasma and molecular gas. It's the regime where atoms begin to combine into molecules and dust grains can condense without being vaporized by radiation. At this temperature, the outflow glows primarily in red and infrared wavelengths, matching the predictions of blackbody radiation laws. Astronomers use the Planck function to model this emission and determine the effective temperature and radius of the expanding photosphere. These measurements often reveal that the photospheric radius can grow to hundreds or even thousands of times the radius of the Sun. A brief spectacular inflation of the merged star's outer layers before they cool and fade. From a physical standpoint, this cooling and color shift tell a story about energy dissipation and transformation. At first, when the merger injects gravitational energy into the envelope, much of it manifests as heat and radiation, making the system shine brightly. As that energy radiates away and the envelope expands, the gas cools, molecules form, and dust begins to dominate the opacity. The redder light we see near the end is essentially the last breath of the event's radiative phase, a sign that the system has entered its quieter post-outburst stage, where the remnant star is obscured behind a dusty shell that slowly drifts into interstellar space. Even though these events fade from view in a visible light, they continue to glow in the infrared for years or even decades. The infrared afterglow acts like a lingering thermal memory of the outburst, allowing astronomers to study how the ejected material evolves over time, how it expands, cools, and interacts with the surrounding interstellar medium. Observations at these wavelengths have confirmed that the dust mass produced in some luminous red novae can rival that created by small supernovae, meaning that these mergers may play a surprisingly important role in enriching galaxies with dust, a key ingredient for future star and planet formation. The red glow of a luminous red nova is not merely a flash in the cosmic dark, it is a slow and deliberate bloom, unfolding over time like a stellar flower. Unlike the rapid, explosive brightness of supernovae or the brief flares of classical novae, the light from a luminous red nova rises gently, builds toward a broad and sustained maximum, and then fades gradually over the course of several months. This slow evolution mirrors the very process that gives birth to it, the merging of two stars and the cooling of their shared envelope, and provides astronomers with a detailed, almost cinematic record of the transformation taking place within. In the earliest stages, as the two stars draw together and begin to share a common envelope, the system emits only modestly more light than usual. The brightness increase is gradual, often spanning several weeks or even months. During this phase, the luminosity climbs steadily as frictional heating within the common envelope converts orbital energy into radiation. Observers tracking these systems sometimes notice small fluctuations in brightness, subtle hints of the chaotic interactions occurring beneath the surface. This stage corresponds to the slow spiraling inward of the stellar cores, where energy is being deposited into the outer layers of the envelope but not yet explosively released. Then comes the moment of merger. When the two cores finally collide and coalesce, the trapped energy in the envelope is suddenly liberated, and the system's luminosity surges to its peak. But even this peak differs from the sharp, short-lived flashes of novae or supernovae. Instead, luminous red novae exhibit a broad, plateau-like maximum, lasting from several weeks to several months. The rise is slow, the summit is wide, and the decline is unhurried, a light curve that reflects a prolonged release of energy rather than a single instantaneous detonation. During this stage, the star may become 1,000 to 10,000 times brighter than the sun, glowing brilliantly in red to near infrared wavelengths. What makes this brightness evolution so fascinating is its multi-phase structure. Many luminous red novae display multiple peaks or fluctuations in their light curves rather than a single smooth rise and fall. These secondary peaks are often caused by complex processes taking place in the expanding envelope, particularly dust formation and shock interactions. As the ejected gas from the merger expands and cools, dust begins to form within it, as described in the previous segment. Initially, this dust can obscure the inner regions, leading to a temporary dip in brightness, almost as if the light of the nova is being extinguished. But as the dust grains re-radiate absorbed light in the infrared, or as shocks within the ejecta reagent parts of the outflow, the system may brighten again, creating secondary or tertiary peaks in the light curve. These re-brightenings can occur weeks or even months after the main peak, giving the impression of a pulsating star in its final stages of transformation. Astronomers have come to recognize this multi-peaked light curve as one of the hallmarks of luminous red novae. In the case of V838 Monocerotis, for example, the brightness increased slowly at first, plateaued for weeks, and then displayed several smaller peaks before fading. Similarly, V1309 Scorpii showed a slow pre-outburst rise that lasted nearly a year before the main eruption, followed by a broad maximum and a gradual decline. These behaviors differ sharply from those of novae, which typically rise rapidly over hours or days, and then decline exponentially, and from supernovae, whose brightness peaks within days due to radioactive decay processes and then fades over months. The slow rise of a luminous red nova's brightness reflects the progressive energy release of the merging process itself. Instead of a sudden detonation, the envelope is heated from within as the two stars spiral together, releasing gravitational energy at a rate determined by their inward motion and the efficiency of frictional dissipation. Once the cores merge, a large fraction of this energy is converted into kinetic energy of expansion, driving the outflow of gas and dust. The optical brightness peaks when the ejected material becomes optically thick, that is, when it absorbs and re-emits light efficiently, creating the illusion of a bright, swollen photosphere surrounding the system. As the envelope expands and thins out, it gradually becomes optically thin, allowing radiations to escape freely, and the visible brightness begins to decline. Yet even as the optical light fades, the total luminosity does not vanish immediately. The newly formed dust in the ejecta continues to absorb visible light and re-radiate it as infrared emission, meaning that while the event may dim in visible wavelengths, it can remain luminous in the infrared for years. This transition marks the second act of the luminous red nova's life, its long-lived infrared afterglow. Telescopes sensitive to infrared light, such as Spitzer or the James Webb Space Telescope, often detect these afterglows long after the optical component has faded, tracing the gradual cooling of the ejected material. The shape of the light curve provides astronomers with invaluable clues about the mass, energy, and geometry of the ejected envelope. A broader and slower peak, for example, suggests a more massive outflow or a slower expansion velocity, while multiple peaks hint at uneven ejection or shock reheating events. In some cases, asymmetric outflows can lead to observable polarization of light, revealing that the explosion was not perfectly spherical, but instead channeled in certain directions, a reminder that even in their elegance, luminous red novae are messy and complex. Quantitatively, the luminosities of luminous red novae typically range from 10 to the power of 5 to 10 to the power of 6 times that of the sun at their peak. The total radiant energy emitted during the entire outburst, integrated over months, can approach 10 to the power of 46 to 10 to the power of 47 ergs, consistent with the gravitational energy expected from the merger of two solar mass stars. These numbers help scientists connect the observed brightness evolution with physical models of stellar coalescence, providing one of the few empirical tests of common envelope evolutions in real time. The fading phase of a luminous red nova is as graceful as its rise. Over several months, the visible light dims, the spectrum shifts deeper into the red and infrared, and the system becomes increasingly dust-obscured. By this point, most of the ejected material is cooled enough to stop radiating strongly in the optical, and the remaining luminosity is dominated by the thermal emission from warm dust at temperatures of a few hundred Kelvin. Eventually, the nova disappears from view in visible light entirely, leaving behind a faint infrared source, a newborn star hidden within a shell of its own creation. The brightness evolution of a luminous red nova, therefore, is a story of transformation told in light. Its slow ascent mirrors the growing energy of the merging stars. Its broad peak represents the moment of union, and its fading tail, the settling of a new equilibrium. Each phase is imprinted in the shape of its light curve, which astronomers study as though reading a diary of a cosmic love story written in photons. These events remind us that not all brilliance in the universe comes in sudden flashes. Some of it arrives gently, builds patiently, and fades with grace, leaving behind not devastation but renewal. The slow rise and fall of a luminous red nova is the universe's quiet declaration that creation itself can be luminous, and that the brightest moments in cosmic history are sometimes born not from destruction, but from union. The evolving light of a luminous red nova is far more than a show of color and brightness. It is a living narrative written in physics, chemistry, and time. Each phase of its glow carries the signature of underlying transformations within the star's expanding envelope. As the outburst unfolds, astronomers trace these changes not only through the light curve, which maps its brightness over time, but also through its spectrum, which reveals the physical and chemical processes shaping the explosion. Together they form a detailed chronicle of a star's death and rebirth, how two stars become one, and how their union radiates across the cosmos. The light curve of a luminous red nova typically begins with a slow and steady rise in brightness. Unlike the rapid, explosive increases seen in novae or supernova, this gradual ascent reflects the slow buildup of energy as the stars spiral together, heating their shared envelope from within. Observers often detect a pre-outburst phase where the system brightens intermittently or displays irregular variations, indicating that mass transfer and envelope interaction have begun. In the case of V1309 Scorpii, for example, the light curve before 2008 showed a slow, irregular brightening that lasted nearly a year, marking the gradual deepening of the binary's contact phase before the final merger. Once the merger is underway, the luminosity increases dramatically, culminating in a broad peak that can persist for weeks or even months. This extended plateau arises because the energy release is not instantaneous. It continues as friction and shocks within the ejected material convert gravitational energy into heat and radiation. The photosphere, the visible surface from which light escapes, expands outward as the envelope inflates, giving the nova its characteristic glowing red hue. The peak itself is often asymmetric, rising more slowly than it fades, a reflection of the gradual heating and more rapid cooling that define the event. Yet the light curve of a luminous red nova is rarely smooth. Many exhibit secondary peaks, plateaus, or fluctuations in brightness. These features correspond to dynamic changes in the ejecta, shocks caused by uneven ejection velocities, or re-brightening from newly formed dust reflecting or re-emitting light. Sometimes the brightness temporarily dips as dust condenses and absorbs visible light, only to rise again when the dust re-radiates energy in the infrared. This multi-peak behavior makes luminous red novae uniquely complex among stellar transients and offers astronomers a window into the chaotic hydrodynamics of stellar mergers. While the light curve tells us how the overall energy output evolves, the spectral behavior reveals the underlying physics of temperature, velocity, and composition. In the early stages of the outburst, when the ejecta are still hot, typically 6,000 to 10,000 Kelvin, the spectrum resembles that of a classical nova, or an early type star. It is dominated by strong hydrogen Balmer emission lines, especially H-alpha, and sometimes by lines of ionized metals like calcium and iron. These emission features originate from hot ionized gas near the photosphere, where energetic collisions excite atoms and cause them to release light at characteristic wavelengths. As time progresses and the ejected material expands, it cools rapidly. The temperature of the photosphere drops from thousands to a few thousand Kelvin, shifting the spectrum from the blue and ultraviolet into the red and infrared. The hydrogen lines gradually weaken, and the spectral energy distribution begins to resemble that of a cool late-type star. Around this time, molecular absorption bands begin to appear, particularly from titanium oxide, TiO, vanadium oxide, VNO, and carbon monoxide, CO. These molecules can only exist at relatively low temperatures, so their presence marks the transition from an ionized plasma to a molecular gas. Titanium oxide in particular leaves a distinctive fingerprint, broad absorption bands in the visible part of the spectrum, giving the nova's light a deeper red coloration. This is why late in their evolution, luminous red novae often display spectra similar to those of red supergiants or Mira-type variable stars. The formation of titanium dioxide and other molecules indicates that the ejected material is cooled sufficiently for complex chemistry to occur, an extraordinary shift from the violent conditions present just weeks before. At the same time, astronomers often detect emission from neutral atomic lines such as sodium and NaI and potassium Ka, which appear as strong doublets in the red part of the spectrum. These lines emerge as the envelope becomes less ionized, as signaling the recombination of electrons and ions into neutral atoms. The velocities of these spectral features, typically a few hundred kilometers per second, also tell us about the speed of the expanding ejecta. These speeds are modest compared to those of supernovae, where material can reach tens of thousands of kilometers per second, but they are consistent with the relatively lower energy release of stellar mergers. As the event enters its cooling phase, the optical spectrum fades while the infrared component strengthens. Observations in infrared wavelengths often reveal emission features from molecules such as CO and H2O, which begin to form in the densest, coolest parts of the expanding shell. These molecules act as precursors to dust grain formation, a process that marks the next stage in the nova's evolution. The spectrum at this stage is typically dominated by broad, smooth continua rather than sharp emission lines, indicating that dust has begun to absorb and reprocess much of the visible light into infrared radiation. One of the most intriguing aspects of the spectral evolution is that it mirrors the temperature decline inferred from photometric observations. Using the blackbody approximation, astronomers can estimate the effective temperature of the photosphere at different stages by fitting the observed spectrum. At peak brightness, temperatures are usually around 4,000 to 5,000 Kelvin, dropping to 2,000 to 3,000 Kelvin as the event fades. These temperatures are consistent with the red color of the emitted light and with the conditions necessary for molecule and dust formation. The evolving spectra also provide critical insights into the structure and composition of the ejecta. For example, the ratio of certain line strengths, such as H alpha to H beta, reveals the density and ionization state of the gas, while the widths of these lines indicate the expansion velocity. In some cases, high-resolution spectroscopy has shown asymmetries in the line profiles, suggesting that the ejection of material is not uniform, but clumpy or directional. This fits with the theoretical picture of the merger process, in which the envelope is expelled in turbulent, uneven waves rather than as a smooth sphere. Over the months following the peak, as the system fades in visible light, its spectrum evolves into what resembles a dust-enshrouded infrared source. By this point, the once bright hydrogen and molecular features have diminished, replaced by the broad thermal continuum of warm dust. Infrared spectra reveal silicate and carbon-rich dust signatures, confirming that this merger not only generated light but also created new solid matter, the raw ingredients for future planetary systems. Taken together, the evolution of the light curve and the spectrum tells a cohesive story. The light curve captures the rhythm of the event. The slow rise, the broad plateau, and the fading tail, often punctuated by secondary rebrightenings. The spectrum provides the melody beneath that rhythm, a gradual transformation from hot ionized gas to cool molecular matter, from blazing blue-white to gentle red and infrared. In unison, they chronicle the physical evolution of the merger, the conversion of gravitational energy into radiation, the cooling and condensation of ejected gas, and the birth of a dust-rich remnant that will continue to evolve for years. Every luminous red nova is, in essence, a light symphony, a performance orchestrated by gravity and time. Its brightness and spectral evolution compose a narrative of creation through collision, where each wavelength reveals a new chapter of the transformation. From the first hydrogen flash to the final whisper of infrared glow, the event tells the same timeless cosmic truth, that even in the wake of destruction there is always a new beginning written in light. As the light of a luminous red nova fades from its peaked brilliance, a quieter but equally profound transformation begins to unfold within the expanding debris. The explosion that once illuminated entire regions of space now becomes the birthplace of new molecules and dust grains, the tiny solid building blocks from which planets, moons, and even life itself eventually emerge. This stage marks the chemical aftermath of the stellar merger, where the energy that once fueled the outburst gives way to a rich interplay of cooling, condensation, and molecular synthesis. In the aftermath of the merger, the ejected material, composed primarily of hydrogen and helium, but enriched with heavier elements from the star's outer layers, expands rapidly into the cold vacuum of space. Initially, the gas is searing hot, fully ionized, and devoid of complex chemistry. However, as it expands, it also cools, dropping from tens of thousands of Kelvin at the onset of the eruption to just a few thousand Kelvin within a matter of weeks. This drop in temperature is critical. It creates an environment where atoms can recombine into molecules, and where these molecules can begin to aggregate into solid dust grains. The first and most abundant molecules to form are carbon monoxide, CO, and water vapor, H2O. Carbon monoxide plays a particularly crucial role in the chemistry of the cooling ejecta. Because of its exceptional stability, CO acts as a natural regulator of carbon and oxygen abundances, binding whichever of the two elements is less abundant and determining what kinds of molecules and dust grains can form afterward. For instance, if oxygen dominates, the excess forms oxides and silicate dust. If carbon is more plentiful, it leads to carbonaceous grains like graphite or amorphous carbon. Astronomers have detected the spectral signatures of CO in multiple luminous red novae, confirming that molecular formation begins astonishingly soon after the outburst. In events like V838 Monocerotis and a V1309 Scorpii, infrared observations reveal the telltale CO first overtone bands, distinct patterns of emission around 2.3 micron meters, emerging just weeks after the eruption. The formation of CO is not just a chemical curiosity, it also serves as an important cooling mechanism. As CO molecules emit infrared photons, they carry away thermal energy, allowing the gas to cool even faster. This rapid cooling, in turn, promotes the condensation of dust grains, accelerating the transition from a glowing fireball to a dust-enshrouded remnant. The creation of dust is one of the most remarkable outcomes of a luminous red nova. As the ejected gas continues to cool to temperatures below about 2000 Kelvin, conditions become suitable for solid particles to condense out of the gas phase. These dust grains form in the densest regions of the outflow, often near the boundary between the hot interior and the expanding cooler shell. Depending on the composition of the progenitor stars, the resulting dust can include silicates, aluminum oxides, iron compounds, and even carbon-rich materials. Each grain begins as a microscopic seed, perhaps only a few nanometers across, that grows as surrounding atoms stick to its surface. The process of dust condensation is complex and highly dependent on local density, temperature, and chemical composition. In some luminous red novae, such as M31 RV and V838 Mon, astronomers observed that the formation of dust coincided with sudden dips in visible brightness, a clear sign that the newly formed dust was absorbing and scattering visible light. As these dust grains absorb photons from the still hot inner regions, they re-emit the energy at longer infrared wavelengths, creating a strong infrared excess in the spectrum. This is why, even after the visible light fades, luminous red novae often remain bright in the infrared for years, or even decades. Over time, the expanding dust shell grows larger and more diffuse. Initially, the dust is optically thick, hiding the newly merged star from view, but as it expands, it becomes more transparent, eventually revealing the rejuvenated star at its center. In the meantime, the dust continues to evolve chemically and structurally. The radiation from the central star can alter the grain's composition, transforming amorphous materials into crystalline forms, or even destroying some dust through sublimation or sputtering. The surviving grains, however, become part of the interstellar medium, where they may one day seed new stars and planets. The importance of dust and molecule formation in luminous red novae extends far beyond the events themselves. These mergers are now recognized as significant contributors to the dust budget of galaxies, particularly in regions where other dust sources like supernova or asymptotic giant branch AGB stars are less dominant. The relatively low expansion velocities of LRND ejecta, typically a few hundred kilometers per second, mean that the material cools slowly and uniformly enough to allow dust to form efficiently. In contrast, supernova ejecta expand so rapidly that much of the gas remains too hot or too diffuse for dust condensation to occur before it's dispersed into space. Thus, luminous red novae occupy a unique niche, slow enough to form dust, energetic enough to spread widely. Infrared telescopes have played a pivotal role in uncovering this aspect of luminous red novae. Instruments such as Spitzer, WISE, and the James Webb Space Telescope have captured the long-lived infrared afterglows of these events, revealing dust temperatures between 300 and 1000 Kelvin long after the optical emission had vanished. In some cases, these observations have shown new dust masses of 10 to the power of -4 to 10 to the power of -2 solar masses, a surprisingly large amount for a single stellar event. This means that each luminous red nova can enrich its surrounding environment with as much dust as a low-mass supernova, albeit through a gentler mechanism. The chemical richness of the ejecta is not limited to carbon monoxide and silicates. As the gas cools, it becomes fertile ground for a wide variety of molecules, SiO, LO, CN, and 2O among them. Some of these molecules have been observed through their characteristic infrared or millimeter wave emission lines, providing further evidence of complex chemistry within the cooling envelope. The formation of these molecules marks a striking transformation, from the chaos of a merger, where temperatures soar high enough to strip atoms of electrons, to a delicate chemical equilibrium, where new molecular species can exist in peace. This molecular and dust formation phase is, in essence, the coda to the luminous red nova's performance. After the fireworks of the initial outburst and the broad crescendo of the light curve, what remains is the quiet aftermath of creation. The light becomes redder, the temperature falls, and the invisible architecture of new matter takes shape. What began as a destructive merger ends as a creative act, producing the raw materials from which future cosmic structures may arise. Astronomers often describe this stage as the alchemy of the universe, the transformation of energy and chaos into structure and substance. In the wake of a luminous red nova, space is left richer than it was before, infused with fresh dust and molecules that will drift through the galaxy, colliding, accreting, and eventually becoming part of new stars, planets, and perhaps even living worlds. In the quiet glow of cooling dust and the faint shimmer of molecular lines, we see the universe's most poetic truth, that every act of cosmic violence carries within it the seeds of renewal. The dust that now drifts away from a luminous red nova is more than debris. It is the beginning of something new, a whisper of creation born from the aftermath of collision. When the powerful merger that fuels a luminous red nova reaches its climax, it sends vast amounts of fast and dust hurtling into space, a monumental exhalation from the newborn star. But unlike the violent, near-instantaneous blasts of a supernova, where matter is flung outward at thousands or even tens of thousands of kilometers per second, the material ejected in a luminous red nova moves at a measured and graceful pace. This difference in speed is not just a matter of scale. It fundamentally determines how the event evolves, how long it shines, and even how it helps shape the chemistry of the cosmos that surrounds it. Typical expansion velocities in luminous red novae range from about 100 to 500 kilometers per second, though some events have been recorded with outer layers reaching as high as 1,000 kilometers per second in their fastest components. By contrast, classical novae can reach velocities around 1,000 to 5,000 kilometers per second, while supernovae routinely exceed 10,000 to 30,000 kilometers per second, with some extreme cases even surpassing 100,000 kilometers per second. The luminous red nova's expansion is therefore modest, almost gentle by cosmic standards, and yet this apparent gentleness is precisely what makes it so fascinating and so conducive to the formation of molecules and dust. To understand why the slower expansion matters, one must consider the interplay between velocity, density, and temperature. In the moments following a stellar explosion, the ejected material expands rapidly into the vacuum of space, converting its internal thermal energy into motion. The faster the material expands, the more quickly it cools, but also the more rapidly it becomes rarefied, losing density. In a supernova, the gas expands so swiftly that while it cools, it also thins out almost instantly, leaving too little time or density for atoms to collide, combine, and form stable molecules or dust grains. Most of the gas remains ionized, and much of the dust that might try to form is destroyed by the intense radiation and shock waves. In a luminous red nova, however, the slower expansion allows the ejected material to cool gradually and uniformly. The dense, thick envelope of gas maintains sufficient pressure and a particle interaction for chemistry to flourish. Temperatures fall to 3,000 to 5,000 Kelvin within the first weeks after the outburst, and then continue to drop steadily as the envelope expands further. These conditions are ideal for molecular recombination, the process through which atoms bond to form stable molecules like carbon monoxide and CO and water, H2O. Soon after, as the temperatures dip below 2,000 Kelvin, these molecules act as condensation nuclei for dust grain formation. The relatively slow expansion rate also means that radiation from the central newly merged star interacts with the ejecta over an extended period. This interaction provides a sustained source of heating and ionization that subtly shapes the light curve and spectral evolution of the nova. Instead of a brief, blinding flash followed by a rapid decline, as in supernova, luminous red nova display broad peaks and long tails in their light curves, reflecting a continuing dialogue between the outflowing material and the light emerging from within. The result is a luminous glow that can persist for months, sometimes punctuated by secondary peaks caused by shocks within the ejecta. Spectroscopic measurements give us precise insights into the velocity of these outflows. The widths of emission lines, particularly hydrogen's H-alpha line, serve as direct indicators of expansion speeds. In most luminous red novae, these lines exhibit Doppler broadening corresponding to velocities between 200 and 400 kilometers per second, with some showing narrow absorption components that trace even slower moving material. Occasionally, multiple velocity components are observed, revealing a layered outflow structure, slower, denser material forming the inner envelope, and faster, lower density material in the outermost layers. This stratification likely reflects the complex sequence of mass ejection events that accompany the final stages of the merger. In events like V1309 Scorpii, the measured outflow velocities were about 150 to 200 kilometers per second, consistent with the expectations for a low-mass stellar merger. In contrast, V838 Monocerotis showed components moving up to 500 kilometers per second, suggesting a higher energy, more massive system. These differences give astronomers valuable clues about the progenitor systems, the masses of the merging stars, their orbital energies, and how efficiently that energy was converted into kinetic motion. The lower expansion velocities also have another profound consequence. They make luminous red novae fertile factories for dust production. Because the ejecta remain dense for longer periods, there is ample time for atoms to stick together, forming complex molecules and condensing into solid particles. The expanding material effectively becomes a stellar laboratory for condensation, where silicates, carbon compounds, and oxides can crystallize into fine grains. These grains, carried outward by the slow but steady flow, eventually enrich the surrounding interstellar medium with fresh dust that may someday participate in the formation of new stars, planets, and even life-bearing worlds. Moreover, the slower expansion ensures that shocks within the ejecta, caused by faster inner layers catching up to slower outer layers, occur at lower velocities and temperatures. These internal collisions, while mild compared to supernova shocks, can reheat localized regions, producing the secondary brightness peaks often observed in the light curves of luminous red novae. Such shocks can also compress gas pockets, further enhancing molecule and dust formation by momentarily increasing density. The measured expansion velocities not only illuminate the physics of luminous red novae, but also reinforce their position as a bridge between novae and supernovae. Energetically, their velocities reflect their intermediate nature. They're very much slower than the explosive outflows of a supernova, but significantly faster than the gentle stellar winds of a red giant. This middle ground is mirrored in their energy output and brightness, both of which fall between the extremes of classical novae and supernovae. As the months pass and the outflow continues to expand, the ejected material gradually thins, and the central remnant begins to emerge. By this point, the expansion velocity ensures that the gas and dust have spread into a vast, cool shell surrounding the newly merged star. This shell, illuminated by residual heat and the faint light of the remnant, glows softly in the infrared, its expansion rate measurable through Doppler shifts and proper motion studies. Observations from instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope are now providing unprecedented detail, allowing astronomers to map these expanding shells and directly track how the velocity profile changes over time. It is the slower pace, the cosmic equivalent of a deep breath rather than a violent explosion, that allows luminous red novae to transform destruction into creation. Their outflows are not the shock waves of annihilation, but the steady dispersal of new material into the galaxy. Each particle of dust, each molecule of carbon monoxide, carries within it the memory of two stars that once circled one another in gravity's embrace and then became one. When we observe the ejecta expanding outward at a few hundred kilometers per second, we are witnessing more than motion. We are watching cosmic transformation in real time. Those clouds of gas and dust, drifting ever outward, are the seeds of future worlds, the quiet echoes of a union that reshape both matter and meaning. The luminous red nova's modest velocity ensures that what it gives to the universe endures. Not only light, but also substance, not only brilliance, but legacy. To truly understand a luminous red nova, one must look at it not just through a single window of light, but through many. From the fiery glow of the optical spectrum to the gentle hum of radio waves, these rare stellar mergers unfold across a vast range of wavelengths, each one revealing a different layer of their story. Like peeling back the veils of a cosmic onion, astronomers study luminous red novae in optical, infrared, and radio light to trace their temperature evolution, follow the birth of dust, and probe the structure of the expanding debris that surrounds the newly merged star. Each wavelength offers a unique vantage point on the same breathtaking transformation. When a luminous red nova first erupts, it shines most brightly in the optical range, the same kind of light visible to the human eye. During these early weeks, the optical emission is dominated by the hot photosphere, the outer layer of the ejected material that radiates light as it expands. The optical observations are crucial because they capture the rise and peak of the light curve, providing the first detailed look at how quickly the nova brightens and how long it sustains its peak luminosity. At this stage, optical spectroscopy allows scientists to analyze the event's temperature, chemical composition, and velocity structure. The early spectra show strong hydrogen emission lines, especially the prominent H-alpha line at 656.3 nanometers, along with features of calcium, sodium, and sometimes iron. These lines are broadened by the Doppler effect, a telltale sign that the gas is racing outward at hundreds of kilometers per second. As time passes, the optical spectrum evolves. The hot ionized features fade, replaced by molecular absorption bands from species like titanium oxide, TiO, and vanadium oxide, VO, indicating that the gas is cooling and transitioning into a molecular state. However, as the luminous red nova cools, much of its energy shifts from the optical into the infrared. This transition marks one of the most significant phases in the life of the nova, the formation of dust. As temperatures in the ejected material drop below about 2000 Kelvin, atoms begin to bond into molecules and then condense into solid particles, microscopic grains of silicate, carbon, and metal oxides. These dust grains absorb the remaining visible light and re-emit it as infrared radiation. Infrared observations are therefore indispensable. They allow astronomers to track the thermal glow of cooling dust and determine its composition, mass, and temperature. For example, after the optical light of V838 Monocerotis faded in 2002, the object remained bright in the infrared for years. Data from the Spitzer Space Telescope revealed a rich infrared spectrum, showing warm dust at temperatures between 300 and 800 Kelvin, radiating strongly even as the visible light declined. Similar behavior was seen in V1309 Scorpii, where infrared telescopes detected new dust forming within months of the merger, confirming that these events are efficient dust factories on a galactic scale. The infrared light curve of a luminous red nova often lingers long after the optical emission has disappeared, acting as a thermal echo of the event. Instruments like WISE, Spitzer, and more recently the James Webb Space Telescope, JWST, have provided high-resolution infrared spectra that reveal not only the temperature of the dust but also its evolution over time. For instance, the JWST can detect the spectral fingerprints of silicates and carbon compounds, allowing astronomers to determine whether the merger produced oxygen-rich or carbon-rich dust. A clue to the original composition of the progenitor stars. Even deeper insight comes from radio observations, which peer into the colder, outermost layers of the expanding debris. When the shock waves generated by the merger interact with surrounding gas, they can accelerate electrons to the near-light speeds, causing them to emit synchrotron radiation, a form of non-thermal radio emission. Detecting this radio signature allows scientists to estimate the density of the circumstellar material and to study how the ejecta interact with their environment. Radio telescopes, such as those in the Very Large Array, VLA, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have begun to capture this faint but revealing emission from luminous red novae. ALMA, in particular, excels at observing molecular lines in the millimeter and submillimeter wavelengths, such as those from carbon monoxide, CO, and silicon monoxide, SiO. These molecular lines provide direct measurements of the velocity, density, and temperature of the cooling ejecta. In some cases, they also show complex velocity structures, evidence of multiple layers or asymmetric outflows. The combination of optical, infrared, and radio data paints a complete multi-dimensional portrait of a luminous red nova's evolution. The optical reveals the eruption's dynamics and chemistry at high temperatures. The infrared uncovers the dust formation and the slow cooling that follows, and the radio exposes the cold remnants and shocks that persist long after the visible light fades. Together, these observations allow astronomers to reconstruct not just the timeline of the outburst, but also the underlying physical processes driving it, from the merger itself to the shaping of the debris cloud. One particularly beautiful example of this multi-wavelength synergy comes from V838 Monocerotis, whose optical images captured by the Hubble Space Telescope revealed a spectacular series of light echoes, rings of light reflecting off surrounding interstellar dust. Meanwhile, infrared telescopes track the cooling dust and expanding molecular gas, and radio observatories map the slower, denser regions of the ejecta. This holistic approach transformed V838 Mon from a mysterious red transient into a detailed case study of a stellar merger in all its phases. Multi-wavelength observation also helps resolve long-standing mysteries about energy distribution. In visible light, a luminous red nova may appear modestly bright, but infrared and radio data often reveal that most of the total energy is hidden in cooler wavelengths. By comparing luminosities across the spectrum, astronomers can estimate the total radiative output, typically between 10 to the power of 46 and 10 to the power of 48 ergs, and better understand how efficiently gravitational energy from the merger is converted into heat and radiation. Monitoring these events across wavelengths also provides a rare opportunity to track stellar evolution in real time. The transition from hot to cool emission, from atomic to molecular spectra, and from smooth optical light to complex infrared and radio behavior all occur within months or years, the blink of an eye in cosmic terms. Every wavelength tells part of this story. Optical light reveals the drama, infrared captures the aftermath, and radio chronicles the enduring legacy of the explosion. In a sense, studying a luminous red nova across different wavelengths is like listening to an orchestra where each instrument plays in a different key. The optical gives us the soaring violins, bright, emotional, and intense. The infrared provides the deep, resonant cellos, carrying the warmth of dust and the echoes of creation. And the radio offers the faint but steady percussion, the low thrum of expanding gas, the final heartbeat of a cosmic union. Together, these harmonies reveal the full symphony of transformation, a stellar duet ending not in silence, but in the creation of something entirely new. Among the handful of luminous red novae ever observed, a few stand out as cosmic milestones, each one offering a unique window into the mysterious process of stellar merger. These rare events, scattered across decades and galaxies, have become the cornerstones of our understanding of this phenomenon. Each tells a slightly different story, revealing new clues about how stars interact, merge, and evolve. Four in particular: V1309 Scorpii, V838 Monocerotis, M31RV, and AT2017 JFAS, represent the most important milestones in the study of luminous red novae, collectively shaping the framework through which astronomers now recognize and study these extraordinary cosmic unions. The case of V1309 Scorpii remains one of the most pivotal discoveries in modern stellar astronomy, the first luminous red nova to be observed forming in real time. Discovered in 2008 in the constellation the Scorpius, V1309 Scorpii at first appeared to be a typical nova, but as the data accumulated, the event defied every expectation. Its brightness rose slowly rather than sharply, and its color grew progressively redder over time. The real breakthrough came when astronomers examined archival data from the optical gravitational lensing experiment, OGLE, which had been monitoring the same region for years before the outburst. Those pre-eruption observations revealed that the progenitor system was a contact binary, two stars so close that they shared a common outer layer. Over 6 years, their orbital period had been steadily decreasing, showing clear evidence that the stars were spiraling toward each other. Then in 2008, the light curve suddenly brightened and peaked. The stars had finally merged. V1309 Scorpii provided the first direct observational proof that a stellar merger produces a luminous red nova. Its light curve captured every step of the process, from pre-merger instability to the final explosion. Spectroscopy showed that after the outburst, the object's temperature dropped rapidly from about 5,000 to 3,000 Kelvin, and its spectrum shifted from hydrogen emission to molecular absorption, classic signs of cooling and dust formation. The event's energy output, about 10 to the power of 46 ergs, was modest compared to other transients, but perfectly aligned with theoretical predictions for a low-mass merger. Today, V1309 Scorpii stands as the archetype of luminous red novae, the Rosetta Stone that allowed astronomers to decode decades of enigmatic red outbursts. Before V1309 SCO clarified the phenomenon, one of the most famous and puzzling examples was V838 Monocerotis, discovered in 2002. Initially mistaken for a nova or even a peculiar supergiant outburst, V838 Mon quickly proved to be something far stranger. Its brightness rose dramatically over several weeks, then lingered, and its color evolved from white to golden to a deep striking red. The most iconic images of V838 Mon came from the Hubble Space Telescope, which captured breathtaking light echoes, expanding rings of light scattering off surrounding interstellar dust. These echoes didn't come from new explosions, but from light reflecting off pre-existing material, allowing astronomers to visualize the three-dimensional structure of the dust cloud surrounding the star. Spectroscopic studies of V838 Mon revealed a sequence of transformations typical of a luminous red nova. Strong hydrogen emission lines at first, followed by molecular absorption features as the temperature declined. Infrared observations showed the formation of new dust with temperatures around 500 to 800 Kelvin and expansion velocities near 400 kilometers per second. Unlike V1309 Scorpii, however, the progenitor of V838 Mon was much more massive, possibly involving a B-type star and a smaller companion. This higher mass explains its greater luminosity, peaking at nearly 1,000,000 times that of the Sun, and its longer-lasting infrared afterglow. The event remains one of the most visually stunning and scientifically rich examples ever recorded, offering insight into how mergers among massive stars differ from those of lower-mass pairs. Long before V838 Mon and V1309 Scorpii illuminated the merger connection, astronomers had already encountered a mysterious red transient that defied classification. M31RV, an enigmatic outburst observed in 1988 in the Andromeda Galaxy, M31. Located near the galaxy's bulge, M31RV brightened to an absolute magnitude of about minus 9.95, making it easily visible even at a distance of more than 2 million light-years. What caught astronomers' attention was its spectral evolution, initially hot and blue, but quickly cooling and reddening over just a few weeks. The event's luminosity and temperature changes didn't match any known nova or supernova behavior, and at the time its origin was a mystery. In retrospect, M31 RV was likely the first confirmed extragalactic luminous red nova, though it would take decades for scientists to recognize it as such. Later reanalysis of archival data, coupled with comparisons to V838 Mon and V1309 Scorpii, confirmed that M31 RV's light curve, color evolution, and inferred energy output were consistent with a stellar merger. Modern telescopes, including Hubble and Spitzer, later searched for remnants of the event and detected faint infrared emission, possibly from cooling dust. Evidence that, like other LRNE, M31RV had produced a dense, dusty shell. Its discovery long before the merger hypothesis was widely accepted makes it a historical cornerstone, proving that these rare events have been occurring and escaping recognition for far longer than we realized. In more recent years, the continued advancement of wide-field sky surveys has brought new luminous red novae to light, including one of the most compelling modern examples, AT 2017 JFS, detected in 2017 in the nearby galaxy NGC 4470. This event showcased all the hallmarks of a luminous red nova, but on a more powerful scale. Its light curve featured the characteristic slow rise, broad peak, and gradual fading typical of the class, while its spectrum evolved from hydrogen emission to strong molecular absorption features as the ejecta cooled. Early observations indicated expansion velocities of about 500 kilometers per second, consistent with a moderately energetic merger. What set AT 2017 JFAs apart was the clarity of its infrared evolution. As the optical brightness declined, infrared telescopes recorded a growing emission signal, evidence of substantial dust formation. Over months, the event became dominated by infrared light, confirming that large amounts of dust were condensing within the outflow. The energy release, estimated between 10 to the 47th and 10 to the 48th ergs, placed it among the most luminous known red novae, suggesting that it may have resulted from the merger of a more massive stellar pair than those responsible for V1309 Scorpii. Its detection also demonstrated how new facilities like the Zwicky Transient Facility, ZTF, and the Gaia satellite are revolutionizing the discovery of these rare events, capturing them early enough for detailed multi-wavelength follow-up. Together, these key examples, M31RV, V838 Monocerotis of V1309 Scorpii, and AT 2017 JFS, illustrate the diversity and unity of luminous red novae. Each event differs in scale, mass, and energy, but all share the same underlying mechanism, the merger of two stars into one. M31 at RV introduced the puzzle. V838 Mon provided the spectacle, V1309 Scorpii delivered the proof, and AT 2017 JFS confirmed the universality of the process. Through these cases, astronomers have traced the full arc of the luminous red nova story, from discovery and confusion to understanding and prediction. Their combined legacy has redefined our view of how stars live and die. No longer are stellar deaths seen solely as explosions or implosions. Some end in union, not annihilation. Each luminous red nova leaves behind a single rejuvenated star, surrounded by a halo of dust and memories of its dual origin. In that sense, these key examples are not just data points in an astronomical catalog, they are cosmic love stories, each recorded in the light of a universe that even in its vastness finds room for creation born from collision. As the light from a luminous red nova fades in the visible wavelengths, the event itself does not truly disappear. It simply transforms its voice. What once roared in brilliant crimson across optical telescopes now whispers softly in the infrared, where its story continues for years or even decades. This phase is invisible to human eyes, but rich with information about the nova's evolution, its cooling dust, and the newborn star it leaves behind. For astronomers, infrared telescopes are not just helpful tools. They are absolutely essential to understanding the full life cycle of a luminous red nova. Without them, we would see only the surface spectacle, the brief optical bloom, and miss the far deeper, quieter processes that follow. The reason for this lies in the physics of dust formation and light absorption. As a luminous red nova expands and cools, it ejects enormous amounts of gas and newly condensed dust into space. Dust grains composed of silicates, carbon, and metal oxides are highly efficient at absorbing and scattering visible light, especially at shorter, bluer wavelengths. However, these same dust particles then re-radiate that absorbed energy at much longer wavelengths. In the infrared range, typically from a few micrometers to a few hundred micrometers. This means that much of the nova's light, once visible, becomes trapped, transformed, and re-emitted as heat radiation. In essence, the visible light vanishes, but the energy remains, glowing faintly and persistently in infrared. Infrared telescopes are designed to detect precisely this kind of emission. They allow astronomers to peer through the dusty veil that obscures the merger remnant, revealing what optical instruments cannot. This is especially critical because after the initial outburst fades, a luminous red nova becomes almost completely hidden in visible wavelengths. The surrounding dust envelope acts like a cosmic cocoon, thick, opaque, and cold. Only infrared light with its longer wavelengths can penetrate this shroud, carrying with it the signatures of the cooling dust and the newborn star nestled at the center. The infrared phase of a luminous red nova typically begins a few weeks to months after the optical peak. As the ejected material expands and cools, dust grains start to condense, initially forming at temperatures of around 1000 to 1500 Kelvin. These hot dust grains emit strongly in the near infrared, wavelengths of 1 to 5 micrometers, producing an infrared flare that may last for months. Over time, as the dust cools to 300 to 800 Kelvin, the peak emission shifts into the mid and far infrared, detectable by space-based observatories equipped to see longer wavelengths. Infrared observations are therefore the key to tracking the dust formation process in detail. By measuring the changing infrared brightness and color over time, astronomers can determine how quickly the dust forms, how much of it is produced, and what its temperature and composition are. For example, after the optical brightness of V838 Monocerotis faded in 2002, the Spitzer Space Telescope detected a strong and persistent infrared excess, revealing large amounts of silicate and carbon-rich dust forming in its ejecta. The dust's temperature declined gradually from about 800 Kelvin to 400 Kelvin over several years, perfectly tracing the nova's cooling history. Similarly, infrared observations of V1309 Scorpii in the years following its 2008 outburst revealed a dense dust shell surrounding the remnant star, glowing at temperatures near 500 Kelvin. The system's optical light had nearly vanished by this time, completely obscured by the new dust. Without infrared instruments, this critical stage of its evolution, the creation of a dust cocoon and the slow emergence of the post-merger star, would have been lost to us entirely. One of the main reasons infrared telescopes are so powerful in this context is their ability to perform spectroscopy, splitting infrared light into its component wavelengths to identify specific molecular and dust features. The infrared spectra of luminous red novae often contain broad emission bands from silicates around 10 and 18 micrometers, and carbon-based compounds around 6 to 9 micrometers, as well as narrow lines from molecules such as SiO, SiO, and H2O. These features allow astronomers to identify whether the ejecta are oxygen-rich or carbon-rich, providing clues about the composition of the original stars and the chemistry of the merger. Infrared spectroscopy can also measure the temperature gradient within the dust shell, revealing how heat is distributed as the ejecta expand. By modeling the infrared emission using blackbody fits, scientists can estimate the total dust mass produced, typically between 10 to the minus 4 and 10 to the minus 2 solar masses. This may seem small, but multiplied across billions of stars over cosmic timescales, such events contribute significantly to the galactic dust budget. Infrared telescopes are thus not only observing transient fireworks, but also documenting the recycling of stellar material that enriches galaxies with the raw ingredients for future star and planet formation. Modern observatories like the James Webb Space Telescope, JWST, have elevated this field to new heights. With its unparalleled sensitivity in the mid-infrared, JWST can peer deep into the dusty remnants of luminous red novae long after their optical light has vanished. Its instruments, such as MIRI, mid-infrared instrument, can resolve the spectral signatures of complex molecules and measure dust temperatures down to a few hundred Kelvin. This allows astronomers to follow the nova's evolution through years, to watch the dust cool, settle, and disperse, and perhaps even glimpse the rejuvenated star that emerges from within. Infrared telescopes also play a crucial role in early detection and classification. Many luminous red novae show infrared brightening even before their optical peaks, as the dust begins to form almost immediately after the first energy release. Surveys like WISE, Wide Field Infrared Survey Explorer, and NEOWISE monitor the sky in infrared, capable of catching these precursors and alerting astronomers to potential merger events that might otherwise go unnoticed. In some cases, infrared light provides the first sign that a stellar merger is underway, even before it becomes visible in optical telescopes. On the longer timescales, infrared monitoring reveals the fate of the remnant star. As the dust shell thins and becomes more transparent, the infrared emission declines, eventually exposing the newly merged star at the center. Observations have shown that these post-merger remnants often shine with infrared excess, a lingering signature of the warm dust that still surrounds them. In some cases, the remnant settles into a stable state, appearing as an unusually red, cool star, while in others the dust continues to dissipate for decades, slowly merging with the interstellar medium. When the brilliant outburst of a luminous red nova finally fades, and its fiery glow sinks beneath the veil of cooling dust, what remains is one of the most poignant and transformative sights in the cosmos. A single newly born star heavier altered and surrounded by the expanding debris of its own creation. The chaos of the merger settles into an unexpected calm, leaving behind the quiet aftermath of cosmic rebirth. Though the dazzling optical light has long vanished from view, this stage marks not an end, but a beginning. The birth of a new stellar entity forged from the death of two. At the heart of this aftermath lies the merged star itself, a single, more massive remnant formed from the fusion of the two progenitor stars that once orbited each other. This remnant is not an ordinary star, it is a hybrid, carrying within it the combined mass, angular momentum, and chemical peculiarities of both its ancestors. In many cases, the new star is significantly larger and more luminous than either of its predecessors. For a time, it may resemble a red or infrared supergiant, swollen and bloated from the excess heat and angular momentum inherited during the violent merger. Its outer layers remain unstable, gradually radiating away the residual energy of the collision until the star finds equilibrium once again. During this period of readjustment, the remnant could exhibit pulsations, irregular light variations, and strong winds as it sheds the last remnants of the common envelope that once bound the two stars together. In some systems, these winds may even continue to drive the slow expansion of the surrounding dust and gas for years or decades after the eruption. Eventually, as the remnant stabilizes, it settles onto a new position in the Hertzsprung-Russell diagram, often appearing as an anomalously bright and red star. Its surface enriched with elements dredged up during the merger, and its rotation often far faster than normal. Encircling this rejuvenated star is the expanding shell of gas and dust, the tangible memory of the merger's violence. This shell, composed of the material expelled during the common envelope phase and the final coalescence, expands outward at speeds of a few hundred kilometers per second, Over time, it stretches into a vast, diffuse bubble, sometimes extending several astronomical units across, large enough to encompass the orbits of planets if such worlds had ever existed in the system before the merger. The shell's density and composition depend heavily on the nature of the progenitor stars, but it typically contains hydrogen, helium, carbon, oxygen, silicon, and other heavier elements. In the first few months to years after the outburst, this expanding material is dense and optically thick, completely obscuring the remnant star from view. The light that escapes comes mostly in the infrared, emitted by the warm dust grains formed in the ejecta. Observations from telescopes such as Spitzer WISE and now the James Webb Space Telescope, JWST, reveal this lingering infrared glow, a thermal echo of the event's earlier brilliance. As the shell expands and cools, it becomes optically thin, allowing light from the central star to leak through. Eventually, after years or even decades, the dust disperses enough for the remnant to reappear in visible light, though often much redder than before. What astronomers find when they finally glimpse this remnant is both beautiful and surprising. The post-merger stars are often overluminous and underdense for their mass, a result of their inflated outer envelopes and the excess internal energy still radiating away. Over time, these stars contract and cool, gradually evolving into stable configurations. Some may become blue stragglers, stars that appear younger and bluer than their neighbors in old star clusters, rejuvenated by the fresh supply of hydrogen mixed during the merger. In other cases, especially when more massive stars are involved, the remnant may evolve into a luminous red supergiant or even eventually end its life in a supernova. The surrounding shell of dust and gas also undergoes remarkable evolution. Initially hot and dense, it radiates strongly in the infrared, but as it expands, it cools and fades. The newly formed dust grains, silicates, carbonaceous particles, and oxides begin to coagulate and drift outward, eventually merging with the interstellar medium. In this way, each luminous red nova contributes fresh raw material to its galactic environment, enriching the cosmos with new dust that may one day seed future generations of stars and planets. In some cases, remnants of these shells can still be detected decades after the eruption, glowing faintly in infrared or radio wavelengths. The structure of the expanding debris can sometimes be irregular or asymmetric, shaped by the dynamics of the merger itself. Hydrodynamic simulations suggest that during the merger, the ejection of mass is not uniform but occurs in bursts and streams, leading to bipolar outflows or ring-like structures. Observations of V838 Monocerotis, for example, have revealed such complex geometry, the dust and gas forming intricate layered shells illuminated by the central star's light. These structures tell us that even in their apparent calm, the aftermath of luminous red novae retains the scars of their chaotic birth. The long-term fate of the remnant depends largely on its final mass and composition. If the merger product is massive enough, it may continue to evolve through further nuclear burning stages, potentially leading to a future core collapse supernova. If less massive, it will slowly contract and stabilize, shining for millions or billions of years as a single main sequence or a red giant star. Either way, it carries forward the combined heritage of its parent stars, a permanent fusion of identities written in light and matter. What makes this aftermath so profound is not just its scientific significance, but its poetic symbolism. Out of the destruction of two stars comes the creation of one, a new, more massive entity surrounded by the debris of its own formation. Where once there were two separate orbits, two distinct cores, and two individual stellar lives, there is now a single reborn star encircled by a halo of dust that glows softly with the memory of their union. It is a reminder that even in astrophysical cataclysm, creation follows collapse, and that the universe in its endless cycles wastes nothing. It only transforms. Over time, as the expanding shell drifts farther into space and the remnant star stabilizes, the visible traces of the luminous red nova fade completely. Yet the legacy of the event endures, imprinted in the interstellar medium as a subtle enrichment of dust molecules and heavy elements. The seeds of future cosmic structures. Each luminous red nova, then, is not merely an ending, or even a single act of renewal. It is a contributor to the ongoing evolution of galaxies, quietly recycling matter and energy in the grand cosmic cycle of birth and death. In this final serene phase, the luminous red nova no longer blazes as a beacon, but hums softly in the background of the universe's perpetual music. Its new star glows, its dust drifts outward, and its light becomes part of the cosmic tapestry. A testament that in the vast, cold, dark, even the most violent unions can leave behind beauty, stability, and the promise of the new beginnings. For decades, astronomers have known that most stars in the universe are not solitary suns like our own. Instead, the majority are born in binary or multiple systems, locked together in intricate gravitational relationships that can last millions or billions of years. The evolution of these systems is far more complex than that of single stars. They can exchange a mass, transfer angular momentum, spiral closer together, or, in rare cases, merge entirely. Yet for much of modern astronomy's history, the idea of directly witnessing such a merger seemed almost impossible. The process was predicted by theory, simulated by computer, but never conclusively observed. That all changed with the discovery and study of luminous red novae, LRNE. These rare cosmic events have provided astronomers with the first unambiguous, real-time evidence of stellar mergers, confirming what had long been suspected but never directly seen. Every observation of a luminous red nova, from the slow pre-merger brightening to the peak of the outburst and the dust-enshrouded aftermath, offers crucial data that helps refine our models of binary star evolution. In a field often limited by indirect observation, luminous red novae represent something exceedingly rare in astrophysics, a clear and direct window into one of the most transformative processes in a star's life. Before LRNE were identified, astronomers relied on theoretical models to understand what happens when two stars share an orbit and eventually coalesce. These models predicted stages like mass transfer, common envelope evolution, and merger ejection, but the details, how energy and angular momentum are exchanged, how much mass is lost, how quickly the merger occurs, remain largely speculative. Luminous red novae change that. By capturing these events at multiple stages and across multiple wavelengths, astronomers have been able to map out the complete timeline of a stellar merger, testing and refining the theoretical framework that describes binary evolution. The most important contribution of luminous red novae to stellar evolution studies lies in their confirmation of the common envelope phase, a critical but elusive stage predicted to occur when one star in a binary system expands and engulfs its companion. Prior to the discovery of V1309 Scorpii in 2008, this phase was understood mostly through models, which suggested that friction within the shared envelope causes the stars to lose orbital energy and spiral inward until they merge or eject the envelope entirely. The pre-outburst data from V1309 Scorpii, showing the orbital period of a contact binary shrinking over time, provided the first observational proof of this theory in action. The subsequent luminous outburst confirmed that the merger had indeed occurred, marking a historic moment for astrophysics. Theory had finally met reality. Since then, other LRNE, such as V838 Monocerotis and AT 2017 JFS, have provided complementary evidence across a range of stellar masses and environments. Each new observation adds a piece to the puzzle, allowing astronomers to study how different types of stars behave during merger events. By comparing these observations, scientists can now investigate how factors like stellar mass, metallicity, and evolutionary stage influence the energy output, luminosity, and duration of the merger. This comparative analysis is refining our understanding of how binary systems evolve over time, whether they merge completely, survive as close pairs, or eventually produce other exotic objects like white dwarf binaries, neutron star pairs, or even gravitational wave sources. Luminous red novae have also reshaped our understanding of angular momentum loss and the mass ejection during mergers. One of the biggest challenges in binary evolution theory is explaining how close binaries lose enough angular momentum to merge in the first place. Observations of LRNE have shown that a large fraction of the orbital energy is converted into the kinetic energy of ejected gas and dust, consistent with models of friction within the common envelope. The measured expansion velocities, typically a few hundred kilometers per second, and the observed energy outputs, 10 to the power of 46 to 10 to the power of 48 ergs, provide concrete numbers that can be plugged into simulations, improving their accuracy and predictive power. Even the light curves and spectra of luminous red novae serve as diagnostic tools for binary evolution. The slow rise and plateau of their brightness, followed by a prolonged infrared phase, reflects the gradual release of gravitational energy rather than a single explosive detonation. This behavior supports models where mergers are extended, multi-stage events, beginning with orbital decay, continuing through envelope ejection, and ending in post-merger stabilization. Spectral changes from hydrogen emission to molecular absorption, meanwhile, give direct evidence of the cooling and dust formation expected during these stages. These data help astrophysicists calibrate radiation hydrodynamic models, bridging the gap between theoretical predictions and observable quantities. Beyond confirming theoretical models, luminous red novae have opened new questions that challenge and deepen our understanding of stellar evolution. For instance, they reveal that mergers are not rare anomalies but rather natural outcomes of binary evolution. Current estimates suggest that as many as 1 in 10 stars may undergo some form of merger during its lifetime, whether through gentle coalescence or catastrophic collision. LRNE then are not mere curiosities. They are a fundamental part of the life cycle of stars. Their study is helping astronomers reassess how many stars in our galaxy have merger origins, how these mergers affect stellar populations, and how they contribute to the diversity of star types we observe today. In particular, LRNE are helping to explain the origins of several previously puzzling classes of stars. Blue stragglers, for example. Stars in old star clusters that appear anomalously young and hot are now thought to be products of past mergers between lower mass stars. Similarly, certain luminous red variables and asymmetric planetary nebulae may owe their peculiar appearances to past merger activity. By linking these evolutionary outcomes to observed LRNE, astronomers are building a continuum of stellar evolution that connects transient events with long-term stellar populations. Luminous red novae also play a key role in connecting stellar evolution to galactic evolution. The dust and heavy elements produced in these mergers contribute to the chemical enrichment of galaxies, seeding future generations of stars and planets. Because their dust forms efficiently and survives the expansion process, LRNE may be important contributors to the interstellar dust content, especially in older or lower metallicity environments where other sources, like massive supernovae, are less frequent. In this sense, studying LRNE helps astronomers understand not just how stars evolve, but how galaxies recycle material over cosmic time. The growing catalog of luminous red novae has even begun to influence gravitational wave astrophysics. Although LRNE themselves are not detectable through gravitational waves, their study helps predict the rates of binary interactions that can eventually produce compact object mergers, the kind that do generate gravitational wave signals. By improving our understanding of how binary stars lose angular momentum and merge, LRNE indirectly helps scientists estimate the frequency of black hole and a neutron star mergers across the universe, linking the quiet light of stellar coalescence with the ripples of space-time observed by detectors like LIGO and Virgo. In short, luminous red novae are the missing observational link that connects theoretical models of binary evolution with the real universe. They are the living laboratories of stellar astrophysics, where processes once thought too slow or hidden to observe can now be studied step by step. Each event adds a new layer of understanding: how stars interact, how they exchange mass, how they spiral together, and how they are reborn as one. Through them, we have learned that the story of stellar evolution is not a solitary one. Stars are not isolated travelers drifting alone through space. They are social, dynamic, and often deeply intertwined. The merging of two stars into one is not just an astronomical curiosity, but a recurring motif in the grand cosmic narrative. And luminous red novae, glowing briefly yet meaningfully in the dark, are the evidence written in light that confirms this universal truth. Even stars evolve together. In the intricate tapestry of stellar evolution, the story of luminous red novae does not end with the merger itself. The aftermath of these events, the swirling dust, the expanding gas, and the newly formed star, often leaves behind structures that are strikingly asymmetric, defying the neat spherical patterns that simple stellar models might predict. These irregular shapes are not mere curiosities. They hold vital clues about the dynamics of stellar mergers and their influence on the environments that surround them. Indeed, the fingerprints of luminous red novae may persist for millennia in the form of asymmetric planetary nebulae, bipolar outflows, and complex circumstellar shells, all of which bear the scars and signatures of their turbulent origins. When two stars merge, the process is inherently chaotic. It is not a clean, symmetric coalescence, but a violent, multi-directional event. As the two stellar cores spiral inward through a common envelope, the ejected material is flung outward under the combined influence of rotation, gravity, and magnetic fields. This chaotic energy release creates flows that are anything but uniform. Instead of a simple spherical shell, the expelled matter forms lobes, disks, jets, and toroidal rings. Shapes reminiscent of the stunning asymmetries observed in many planetary nebulae and other evolved stellar remnants. The common envelope phase, central to the luminous red nova process, plays a pivotal role in generating these asymmetries. As the companion plunges deeper into the envelope of its partner, drag forces and angular momentum transfer produce directional ejections. If the merging stars possess a strong rotational axis, or if magnetic fields channel the outflow, the envelope can be expelled preferentially along certain directions, giving rise to bipolar structures. Observations of several LRNES have revealed these features indirectly. Their light echoes, polarization measurements, and emission line profiles all point toward asymmetric ejecta rather than perfectly spherical explosions. For instance, the spectacular light echoes of V838 Monocerotis provided a three-dimensional glimpse of its surrounding dust and gas, showing layered asymmetric shells that expand at varying speeds and densities. While part of this structure originated from pre-existing interstellar material, the geometry of the echoes suggested that the eruption itself was not uniform, implying directional mass ejection during the merger. Similar asymmetries have been inferred from V1309 Scorpii, whose post-outburst spectral lines revealed multiple velocity components, slower moving material near the equatorial plane, and faster outflows along the poles, hallmarks of a bipolar ejecta system. These findings have led astronomers to propose that stellar mergers like luminous red novae may be responsible for shaping many of the asymmetric planetary nebulae we observe throughout the galaxy. Planetary nebulae, the glowing shells of gas ejected by dying low to intermediate mass stars, often display intricate non-spherical structures, twin lobes, rings, or hourglass shapes. The exact mechanism behind these asymmetries has long puzzled scientists. Single-star models predict that such nebulae should be roughly spherical, yet only a small fraction actually are. The rest, remarkably, show the same kind of complex morphology seen in merger simulations, and LRN ejecta. The link between luminous red novae and asymmetric planetary nebulae is further strengthened by hydrodynamic modeling. Simulations of common envelope mergers show that as the engulfed companion spirals inward, it transfers angular momentum to the envelope, launching powerful equatorial flows and collimated jets. These interactions can create a dense, disk-like structure around the equator of the merged star while simultaneously expelling gas along the poles. Over time, as the star evolves and ionizes the surrounding gas, these bipolar or ring-like shapes become visible, resembling many observed planetary nebulae, such as the Dumbbell Nebula M27 or the Butterfly Nebula M2-9. Even beyond planetary nebulae, luminous red nova remnants might contribute to the formation of complex circumstellar environments seen in other astrophysical systems. In some post-merger stars, the leftover angular momentum and residual accretion disks may drive episodic mass loss or even launch jets, similar to those observed in young stellar objects or evolved giants. These jets can carve cavities and shock fronts into the surrounding material, producing asymmetric emission patterns that remain visible long after the initial outburst. Over centuries or millennia, these features can evolve into large-scale nebular structures, fossil records of the merger's violent past. Infrared and radio observations have begun to detect hints of such structures around known LRN remnants. The expanding dust shells often show non-uniform brightness and temperature distributions, implying clumping and directional outflows. In the case of M31RV, for example, long-term infrared imaging revealed a patchy dust environment inconsistent with smooth spherical expansion. The same was true for V838 Mon, whose post-eruption environment displayed evidence of both pre-existing dust asymmetry and newly formed structures shaped by the merger. These asymmetric remnants also have important implications for stellar population synthesis and galactic evolution. Because mergers can create stars with unusual compositions, rotation rates, and mass distributions, their remnants do not always evolve along the predictable paths of single stars. Some may develop into rapidly rotating giants, while others may retain equatorial disks that influence subsequent mass loss. Over long timescales, these traits can alter the chemical and structural makeup of stellar populations, enriching galaxies not only with dust and heavy elements, but with diverse morphological structures that persist long after the merger has faded. The study of luminous red novae has therefore given astronomers a new way to explain why so many stellar environments look as beautifully irregular as they do. The chaotic physics of mergers, the spiraling dance of gravity, the friction of common envelopes, and the explosive expulsions of mass naturally produce the asymmetries we observe in a wide range of cosmic phenomena. You have from planetary nebulae to supergiant shells, from infrared bubbles to molecular clouds. The fingerprints of mergers are everywhere once you know how to see them. Moreover, the asymmetric nature of LRN remnants helps astronomers understand how angular momentum is redistributed during stellar evolution. The presence of bipolar outflows, equatorial disks, and clumpy ejecta provides direct observational evidence for how rotational energy and orbital dynamics shape the final appearance of dying or merging stars. These insights, in turn, feed back into improved models of stellar mass loss, a critical factor in determining a star's lifetime, luminosity, and ultimate fate. In this way, luminous red novae act as natural laboratories for studying how complexity arises from simplicity in the universe. Two stars begin their journey as an ordered gravitationally bound pair. Over time, interactions between them, mass exchange, tidal friction, and angular momentum transfer lead to instability, chaos, and an eventual merger. From that chaos emerges not a simple spherical remnant, but a layered, asymmetric structure of astonishing beauty. A nebular monument to their violent union. Detecting a luminous red nova is like trying to catch a whisper in a hurricane, fleeting, easily mistaken, and often drowned out by brighter cosmic noise. Despite their immense physical energy, these events are surprisingly subtle when viewed from Earth, and their very nature makes them some of the most challenging phenomena in astronomy to identify and confirm. Each one unfolds slowly, evolves unpredictably, and often hides beneath veils of dust and distance. Out of the billions of stars in our galaxy and beyond, only about a dozen luminous red novae have ever been conclusively observed. Not because they are extraordinarily rare in occurrence, but because they are extraordinarily difficult to see and classify. There are three fundamental reasons for this challenge: their faintness, their short-lived visibility, and their confusing resemblance to other types of stellar outbursts. Combined, these factors mean that most luminous red novae slip through the cracks of our surveys, their brief glow lost amid the endless sea of transient cosmic events. First and foremost, luminous red novae are relatively faint compared to other explosive phenomena. A typical LRN peaks at an absolute magnitude between -9 and -13, roughly 1,000,000 times the brightness of the sun, dazzling by human standards but modest in astronomical terms. Supernovae, by contrast, can reach magnitudes of -17 or brighter, shining tens of thousands of times more intensely. This difference means that a luminous red nova observed in a distant galaxy may appear only as a faint reddish speck, easily mistaken for a dim variable star or overlooked entirely in sky surveys designed to catch brighter explosions. Even within our own Milky Way, interstellar dust and gas can obscure them further, especially since these events tend to recur in dense, star-forming regions where extinction is high. Adding to the difficulty, luminous red novae are transient. Their visible light lasts for only a brief window of time before fading away. The optical outburst, which marks the most luminous phase of the event, typically endures for a few weeks to a few months. After that, the object cools, reddens, and transitions to emitting primarily in the infrared. Without constant monitoring, it's easy to miss this narrow phase when the nova is at its brightest and most distinguishable. Ground-based telescopes with limited observing schedules might catch the tail end of a light curve when the event already resembles an ordinary variable star. And because the later infrared phase is invisible to optical instruments, many luminous red novae vanish from view before they can be properly followed up. Even when these events are detected in time, identifying them correctly poses another major challenge. Their light curves and colors can mimic those of other, more common transients, leading to frequent misclassifications. For example, early in their evolution, LRNEI can resemble classical novae, which are nuclear explosions on the surface of white dwarfs. Both brighten over days or weeks and display hydrogen emission lines in their spectra. However, novae are much hotter and bluer, while LRNES become progressively redder as they cool. Distinguishing between the two requires continuous multi-wavelength observation, something not always possible when the transient is faint or discovered late. Luminous red novae can also be confused with certain types of supernovae and intermediate luminosity red transients, ILRTS. Some supernova imposters, like eruptions from luminous blue variables, LBVS, produce light curves and spectra that closely resemble LRN and AS in their early phases. ILRTS, such as SN 2008S-like events, also inhabit the same brightness range and can show similar color evolution. The only way to definitively separate these phenomena is through long-term monitoring, tracking the object's temperature, spectral features, and fading behavior over months or even years. LRNE tend to evolve toward cooler temperatures, down to 3000 to 4000 Kelvin, and produce strong molecular absorption features, while ILRTS and LBV eruptions typically maintain higher temperatures or different chemical signatures. Another complicating factor is their rarity and unpredictability. Luminous red novae do not follow predictable cycles like pulsating variable stars, nor do they give clear advance warning before eruption. Even in binary systems that are known to be in contact or unstable, predicting exactly when a merger will occur is nearly impossible. The case of V1309 Scorpii, whose merger was only identified after the fact using years of archive data, demonstrates how easy it is to miss the early stages of these events. The OGLE dataset that captured its pre-merger evolution was a stroke of observational luck. Without it, the event might have been dismissed as an ordinary nova. Beyond their inherent faintness and brief visibility, the environments in which LRNE occur often make detection even more difficult. Many of these mergers happen in regions crowded with stars, dust, and gas, star-forming clusters, spiral arms, or galactic bulges, where background light and extinction can obscure subtle changes in brightness. In galaxies like Andromeda, where M31RV occurred, or M85, the dense stellar fields create significant confusion, making it difficult to isolate faint transient sources. Infrared telescopes can sometimes penetrate these dusty regions, but even then, limited observing time and field coverage mean that many events remain undetected. Astronomers also face technical and logistical challenges when trying to confirm a luminous red nova. To confidently classify an event, researchers need multi-wavelength coverage, optical, infrared, and sometimes radio, and long-term photometric and spectroscopic monitoring. However, the coordination required to achieve this across observatories and instruments is enormous, especially for faint, short-lived events that might only be visible for a few nights. Automated transient surveys like the Zwicky Transient Facility, ZTF, and the All-Sky Automated Survey for Supernovae, ASASSN, have made great strides in this area, but follow-up infrared observations are still relatively rare. As a result, many potential LRNE candidates are detected but remain unconfirmed, their nature uncertain due to incomplete data. Furthermore, the dust that forms during and after the outburst creates additional complications. As dust begins to condense in the cooling ejecta, it absorbs visible light and re-emits it as infrared radiation. From an optical perspective, the event seems to fade faster than expected, sometimes leading astronomers to believe it has ended, when in fact it is still active in longer wavelengths. Without infrared monitoring, such dust-obscured phases go unnoticed, and the event can be misclassified or entirely missed. Even the timescale of discovery and publication can hinder identification, because LRNE evolve over months or even years. Confirming their true nature requires patience and sustained observation. Many transient surveys prioritize faster, brighter, or more explosive phenomena like supernovae or gamma-ray bursts, which produce immediate dramatic signatures. By contrast, a luminous red nova's slow evolution can seem unremarkable at first glance, causing it to be overlooked until much later when it has already faded. All these factors combine to make luminous red novae some of the most elusive objects in the modern astronomical catalog. Their faintness, fleeting optical presence, and deceptive similarity to other transients create a perfect storm of observational challenges. And yet, precisely because they are so difficult to detect, every confirmed luminous red nova carries immense scientific value. Each one expands our understanding of stellar mergers, offering rare, direct evidence of a process that occurs countless times throughout the cosmos, but is almost never seen. Thanks to advances in all-sky surveys, improved infrared instruments, and growing awareness of their unique signatures, astronomers are finally beginning to catch more of these rare events in action. The coming years, with the full operation of next-generation observatories like the Vera C Rubin Observatory's LSST legacy survey of space and time, promise to bring a revolution in our ability to detect and study them. But for now, luminous red novae remain cosmic phantoms, dim, red, and transient, glimpsed only occasionally, yet carrying within them the story of how stars embrace, merge, and are reborn. In the vast expanse of the night sky, the universe is never still. Stars pulse, galaxies collide, and cosmic flashes ignite and fade in an endless rhythm of creation and destruction. For most of human history, these transitory events, so as the brief, extraordinary moments when the universe changes before our eyes, went unnoticed, but that is no longer the case. In the 21st century, astronomy has entered a new era of continuous all-sky observation, and this revolution has transformed our ability to detect and study some of the rarest phenomena in existence, including luminous red novae. Today, cutting-edge observatories such as Gaia, the Zwicky Transient Facility (ZTF), and the forthcoming Vera C Rubin Observatory's Legacy Survey of Space and Time (LSST) are changing everything we know about how stars live, die, and merge. These automated wide-field surveys are systematically scanning the heavens night after night, recording billions of sources and searching for the faintest signs of change. In doing so, they are uncovering more luminous red novae, and doing so earlier, more accurately, and in greater detail than ever before. Each of these facilities plays a distinct but complementary role in this ongoing exploration. Gaia, operated by the European Space Agency, was originally designed to chart the most precise three-dimensional map of our galaxy ever made, measuring the positions, distances, and motions of over 1 billion stars. But Gaia's sensitivity and regular scanning of the sky have made it a powerful transient detector as well. Its ability to detect subtle changes in stellar brightness allows it to identify stars entering the early stages of instability, the precursors to events like luminous red novae. Gaia's alert system, which continuously updates with new transient candidates, has already detected several red transients that may represent early or faint mergers. Moreover, Gaia's precise distance measurements allow astronomers to determine the absolute luminosities of these events with unprecedented accuracy, helping distinguish LRNE from imposters such as novae or supernovae. Meanwhile, the Zwicky Transient Facility, ZTF, operating at the Palomar Observatory in California, has become one of the most prolific transient hunters on Earth. Using a 48-inch telescope equipped with a massive 47 square degree field of view camera, ZTF scans the entire northern sky every 2 nights. Its mission is to catch anything that changes, from near-Earth asteroids to supernovae to the faint, slow glow of luminous red novae. ZTF's strength lies in its speed and coverage. It produces terabytes of data each night, and automated algorithms flag potential transients almost immediately. When ZTF detects a candidate LRN, follow-up observations with other telescopes, especially in the infrared, can begin almost at once, ensuring that astronomers capture the early rise and evolution of the light curve that define these events. It was facilities like ZTF that made the discovery of recent candidates such as AT 2017 JFS possible. The event's slow, red brightening and extended light curve were caught early enough to follow its transformation in detail, from optical to infrared phases. Without such wide-field surveys, it would have likely been missed or misclassified. ZTF's growing catalog of red transients provides researchers with the first statistically meaningful sample of luminous red novae, allowing them to analyze patterns and differences across multiple cases. A crucial step toward developing population models for stellar mergers. But the most transformative leap in this field is yet to come. When the Vera C Rubin Observatory's LST begins full operations in the near future, it will usher in an unprecedented era of discovery. Located in Chile's Cerro Pachón, the Rubin Observatory will survey the entire southern sky every few nights with a 3.2 gigapixel camera, the largest digital camera ever built for astronomy. LSST is expected to generate tens of terabytes of data per night, detecting millions of variable and transient objects across a 10-year mission. Among these will be not only thousands of supernovae, but also hundreds of luminous red novae and merger candidates, including many too faint or distant to have been detected before. What sets LSST apart is not just its sensitivity, but its ability to provide continuous, long-term monitoring. Luminous red novae evolve slowly compared to most transients, with light curves stretching over months or even years. LSST's decade-long survey will allow astronomers to follow these events from their earliest precursors, the quiet orbital decay of binary stars, through the eruption itself and into the cooling, dust-enshrouded aftermath. This unprecedented timeline will give scientists a complete view of the merger process, from beginning to end, across many different systems. These observatories working together are transforming our understanding of LRNE in several key ways. First, they are helping astronomers identify the pre-merger behavior of binary systems. Continuous sky monitoring has revealed that many luminous red novae are preceded by slow, irregular brightening, the result of orbital decay and mass transfer between the two stars before the final merger. By catching these pre-outburst signals, telescopes like Gaia and LSST can provide early warnings, allowing researchers to focus additional instruments on the system before it erupts. This makes it possible for the first time to observe the entire sequence of a merger event rather than only its explosive conclusion. Second, these facilities are enabling multi-wavelength coordination between observatories around the world. When a candidate LRN is detected in optical light by ZTF or Gaia, infrared telescopes like JWST, Spitzer and its archival data, or ground-based IR facilities can quickly follow up, capturing the formation of dust and the cooling of the ejecta. Radio observatories like ALMA and the Very Large Array LA can then track molecular emissions and expanding outflows. The result is a holistic, multidimensional portrait of each event, showing not only how it looks, but how it behaves across the electromagnetic spectrum. Third, and perhaps most importantly, these new surveys are quantifying the frequency and diversity of luminous red novae. For decades, the small number of observed cases made it impossible to know whether these events were truly rare or simply underdetected. Now, as more candidates are discovered, patterns are emerging. Some LRNA appear brighter and more energetic, hinting at mergers between massive stars, while others are faint and slow, likely involving lower-mass binaries. By compiling large samples, astronomers can finally begin to construct a taxonomy of stellar mergers, understanding which types of stars merge, how often, and what kinds of remnants they leave behind. Beyond their immediate discoveries, these surveys also fuel theoretical and computational advancements. With real-time data from multiple LRNE, astrophysicists can refine hydrodynamic simulations of common envelope evolution, improving models of how angular momentum and energy are redistributed during mergers. These models, in turn, help predict the observable properties of future events, brightness, color, duration, and even potential gravitational wave signatures from close binary interactions. The synergy between observation and theory is creating a new era of predictive stellar astrophysics. One day soon, astronomers may not only detect luminous red novae as they happen, but anticipate them, identifying unstable binaries and forecasting their inevitable union. Ultimately, the ongoing efforts of Gaia, ZTF, and LSST are helping humanity see something we were once blind to, the quiet, intimate moments of transformation that shape the lives of stars. These telescopes are revealing that the universe's most profound changes do not always announce themselves with blinding explosions. Sometimes they unfold gently, redly, in the merging of two stellar hearts. And as our instruments grow sharper and our gaze more constant, we are beginning to witness the cosmic truth luminous red novae have always whispered. That creation and destruction are not opposites, but partners in the same eternal dance. Through the eyes of modern astronomy, we are learning to see that dance in exquisite detail, one merger at a time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.